It's only a hobby vitamin. Vitamin. America is much more segregated. Doesn't have as much mixing between more slaves and from slaves. Black Americans is as bad as it is in Brazil.
No, but we say that they are. So I don't know. My impression is really like, oh, why do they? The video of communities probably.
Yeah, no, it's absolutely.
Where's the name comes from?
Well, white Americans are obsessed with their connections to Europe.
Yeah, because there are some on average, I think they more. And for the same.
But sure, even in white, there's often not many slaves.
But that's what
It's not true.
I guess the
Very.
just by seeing the especially in the just serious. If the answer is right, if you ask them, just by the face and say it gives you responsibility. But yeah, no, the ground are very large.
And for people who are from this test, they're very motivated. Like you US test is this town has for black people be like up to yeah. The problem is these companies are based on the clientele and the understanding of like ancestral trees of clientele, right? So those are lost.
There's also a question, just the usual question in data science. If you don't have a lot of data, it doesn't work very well. Hey, morning. Zoom. So you need to authorize. I think I'm in the waiting room. I think you need to just authorize.
We have that was good. Okay.
One thing that the United States is claiming they have some sort of indigenous heritage. Like, oh,
Oh,
my
yeah.
great grandmother. So it's almost always not true.
Yeah.
But it's this kind of way to be more authentic or something.
Yeah. Guess that's among the younger generation part.
Good morning. So we have the last session of Bruno.
Okay, yeah. Hello, everyone. So let me start by doing a brief recap of where we were last time. So we introduced empirical risk minimization in the context of supervised learning. And then we introduced some questions that we would like to understand about neural networks. And we started looking at one of these questions, which is about overparameterization and overfitting. So why don't these heavily overparameterized neural networks overfit the data? And then we motivated this by like the bias variance trade-off, which is a folklore in statistics. I introduced it, I discussed it, and then I showed these plots of experiments in neural networks that show that actually the bias variance trade-off doesn't hold. Actually, you have two regimes, one regime where you have kind of a bias variance trade-off, and then if you keep increasing your network, the generalization error keeps going down. And we would like to understand that, like why this is the case. Is it something special about neural networks? Is it something that maybe we missed out in classical statistics? So why it took so long for us to understand that? So this is what is called the double descent. And then we started looking this into a particular model. So let's say, I would say the simplest model of actual neural network where you can consider overparameterization. So if you know something about statistical physics of learning, probably you have come across the perceptron, which is like a single neuron. And a lot of things have been studied in the perceptron, but one thing you cannot discuss in the perceptron, it's the overparameterization, because the perceptron is just one single neuron, so you cannot really talk about, the notion of number of parameters is not so clear there. Actually, you could think about the weights as being dimension d being the number of parameters, but this is also the dimension of the data. And as you saw, the sample complexity is the ratio between the quantity of the data and the number of dimensions. So increasing the number of parameters in the perceptron is also increasing the complexity of the data. So you don't have a decoupling between these two notions. So the first model where you have a meaningful separation between, let's say, parameter count and complexity of the data is the two-layer neural network. And then we introduced it and we said, let's study that. And empirical risk minimization on the square loss. Then we discuss about the classical approach for that problem, which is uniform convergence bounds. We discuss why they are limited. And then we moved on to more of a statistical physics approach where you're going to make strong assumptions, but you're going to try to get tight results. I introduced what is called the multi-index model, which is one class of models for data that you're going to be considering here. And I try to motivate that this model is good enough to capture some notion of the manifold hypothesis, that even though the data is high dimensional, actually the information in the data is contained into a subspace, which is linear, but then you apply a nonlinearity, and then that's what kind of makes it hard to invert this relationship. And many models that we like are subsets of that. and also is a good model because two-layer neural networks are part of this class of models. So meaning that we can meaningfully talk about learning this model with a two-layer neural network. Whether if you get something more complex, we would have a part which would maybe not be captured by the neural network. So this is what we call the teacher-student framework, where we can have a notion of matching between the complexity of the task and the hypothesis class we choose. So we started our investigation of this model by looking at a particular limit, which is simple, but not that simple, in which the first layer weights are fixed. You take them at random and you fix them. So that's what is called the random features model in the machine learning literature. And so this simplifies our life because it removes one of the difficulties of studying neural networks, which is the lack of convexity of the objective function. Of course, it's a major simplification, and one should not stop there, but it's a first step. So this problem is a convex problem. It admits a unique solution. Because the loss is quadratic and I chose a quadratic regularization, the solution is closed form. This becomes a random matrix theory problem. However, on a class of matrices which is slightly more complicated than the ones that we are usually dealing in random matrix theory, because it involves a nonlinear function of the product of two random matrices. So that's the challenge. And towards the end of the lecture, we saw this idea that what really makes this hard is the nonlinearity. So let's linearize it. So you choose a basis which is adapted to the functions. So these are functions on this variable. So conditionally on one of them, this scalar product is Gaussian. So the Hermite polynomials is a good basis for expanding these functions because they are orthogonal with respect to expectations over Gaussian inputs. So this defines like our orthogonal decomposition into low frequency modes, high frequency modes, and they are orthogonal to each other, just like Fourier, but now for like Gaussian inputs. Okay, so we saw that actually high frequency modes are decaying faster with the dimension, and the consequence of that, we computed the moments, and we saw that the moments are also decreasing the dimension. And as a consequence of that, we have this notion of a Gaussian universality. Let me go to it, which is that if I want to compute the generalization error of the original problem with the nonlinear features, is equivalent to computing the generalization error of a Gaussian equivalent model, where actually the data has been generated by fitting, like by a Gaussian random matrix, which has the same mean and covariance as the original matrix. So I just need to keep information about the mean and the covariance in order to compute the risk into this proportional limit. So if you would like to go beyond this proportional limit, you need to keep more information. But in this proportional limit, which is the limit that we often study in statistical physics, it's as simple as just keeping the mean and the variance. And I discussed some generalizations of that in the literature. So this result is relatively recent. I mean, definitely for the machine learning standards. And this result leads us to this formula. So I'm not going to go into detail. I mean, I'm just putting here to show you that this can be done. But once you get rid of the non-Gaussianity, and now you say that your model is equivalently Gaussian, we can just apply the tools that we are using in statistical physics for dealing with random matrices. So these formulas we have derived with Federica Gerace, Marc Mézard, Lenk, and Florent, using the replica method in 2020. And you get the usual self-consistent equations for the summary statistics that characterize the error. So just like in the Curry-Weiss model in the first lecture, but instead of having one magnetization, here we have 8 parameters. It's still 8 is less than d, which is going to infinity. So we are still happy because we can put this in the computer. We can self-consistently integrate it. Once we solve the equations, we can plug in the generalization error. The generalization error is a function of the solutions of these equations. Because the problem is convex, this is replica symmetric. And because it's replica symmetric, means that these equations are contractive and you just have one solution. So you just solve them, get the solution, and put here. There's no metastability because of convexity, essentially. By the way, maybe I say something which is a bit misleading. So if you have convexity, implies replica symmetry, right? But replica symmetry doesn't imply convexity. As we saw, we can have replica symmetric problems in the Bayesian inference context, for example, which have metastability. But here, convexity is going to imply replica symmetry. Okay, so I'm not going to go into the derivation of that. You can find this in the papers or in the lecture notes. But I want to discuss what you get once you plug these equations and you solve them in the computer. So you get these curves. So these are theoretical curves. So here I'm showing on the top is the generalization error. On the bottom is the training error. And the blue curve is for the square loss. And actually, you can generalize everything that I said to a generic convex loss. The replica method actually doesn't care about the loss function. So if the loss is quadratic, you can use this random matrix theory argument that I showed you, and you can do random matrix theory. So actually, you don't need replicas if you like random matrix theory. But the replica method is completely agnostic about the loss function. As long as it is convex, we have replica symmetry, and we can show that this result is exact. But you can also derive results for other loss functions. So here I'm showing the red curve is for the logistic loss for a classification problem. So both these curves display this phenomena that we discussed before, which is this double descent. So here I have the width. So the width is kind of the number of parameters in the network. So it's P, what I call P. And here you have the error. As you increase P, first you go down. Let's focus on the blue curve. First you go down, then you go up. So this is just the bias variance trade-off. Then at some point, you get a peak. And your error is maximum at this peak. Actually, you should go a bit more up. And here's because, I'm taking lambda finite but small. But the smaller I get, the larger this peak gets. And this peak happens precisely where the training error goes to 0. So where you start interpolating the data. So exactly as we observed for the experiments of neural networks, the worst possible error when you overfit more is when you start completely, you have just enough parameters to fit the training set. But then as you keep increasing it, the error keeps going down, as we saw before. And we call this phenomena benign overfitting. So you overfit, but it's not bad. It's benign. And the same thing happens for the logistic loss. So it's just the peak is a bit before, and the peak doesn't go up to the maximal error. So it's just like kind of a cusp in the curve. But again, this cusp happens exactly at the point where you perfectly fit the training data. So that's very nice. We have a theory for that. Can we kind of understand why this is the case? Why this curve looks this way, right? Because, okay, it's nice. We have the formulas, we have the solution, we have the model, we have the curves, but we want to understand why intuitively, why the bias variance trade-off is violated and still you generalize. Okay, so let's take a closer look. Let's focus on the square loss in this random matrix theory part. And let's try to think how this thing looks in terms of the loss landscape. So essentially, you're doing linear regression on these nonlinear features, right? So in linear regression, you're essentially trying to fit, you're trying to solve a system of equations, and you have p parameters, and you have n equations. So n is the number of data points. Each data point gives you a constraint, and you have p parameters to satisfy this constraint. So when p is less than n, you are underparameterized. You cannot find any solution that satisfies all the constraints. So the loss landscape is like, there's a unique minima, but this minima is not at 0 loss. So you cannot interpolate when you have less parameters than the number of data points. Okay, so this is easy to understand. And that's pretty classical. Now, when you hit the point where you have enough parameters to fit the equations, that's when this matrix phi becomes invertible. And actually, you start to be able to interpolate the data. And this is where the peak happens. This is where the interpolation starts. And if you know a little bit about random matrix theory, you see that this is exactly when you have some singularity on the spectrum. And then as you start increasing the number of parameters, you have more parameters than equations, meaning that you can fix all the constraints, but there are many solutions for all the constraints. There are, a lake of solutions. So the problem is convex. So there cannot be local minima. But convex doesn't imply uniqueness, right? It's not strongly convex. So you have a lake of solutions, and this lambda going to zero limit picks one solution, specific solution in this lake of solutions, right? It's the one given by the pseudo inverse of phi. And so we have this lake, and the solution that we are seeing from the replica equations is one of them. But there are other ones.
Try on the edge.
Oh yeah, I always get this question, like it's a
Dynamics, yes, right? This regularization, I would.
exactly, but I'm going to connect to the dynamics. But for now, it's just it doesn't need to be in the edge. There's no reason to be in the edge, but there is a reason to be in the edge. We're going to get there. But yeah, I use the same slide. I should change that because I always get this question. Okay, so what is special about this solution that we are getting when lambda goes to zero, right? When the regularization is going to zero. So if you have done some linear algebra, you know that the lambda going to zero limit of this regularized problem goes to the least squares, and the least squares solution in this regime is the one that have minimal L2 norm. Okay, so it's the pseudo inverse. The pseudo inverse of a matrix is the solution which have the smallest L2 norm. So this is this solution that I'm plotting here in the boundary of the loss landscape is the minimum L2 norm solution. There are many solutions, but one of them has the least norm, and this is the one I'm picking by taking this limit. And that solution, has some properties, like there's a bias, right? Among all solutions, you're picking one, so you're biasing your method, and this bias turns out to be not too bad because in this region is this solution that is generalizing well, right? Now, there are other solutions in the loss landscape. They have higher L2 norm. But because the risk is quadratic, this solution is not necessarily going to have this nice behavior. And actually, here I'm going to show there is one solution out there which is going to overfit. It's a solution that has a very, very large L2 norm, right? So I could pick another solution that overfits. But this solution doesn't overfit because it has a bias. This bias is what we call an implicit bias. It's a bias that, maybe when you chose the method, you didn't think you were cooking a bias, but in the end, by choosing a procedure of minimization, which is you minimize with a lambda and then you take lambda to zero, you are choosing a property implicitly that you might not have expected. Of course, if you know all of these, you expect, and why this solution, why I'm stressing this solution and not another solution? Why did I choose the lambda lambda norm square and then I took lambda to zero? I could have put anything else there, right? The reason is, it turns out that if you don't take any regularization, so you just consider the vanilla problem. Oh, this doesn't erase. Okay, maybe I should choose another one that erases better. So if you just consider the vanilla problem, which is minimum over, what is my notation? Did I call the A? A in RP of 1 over n, sum over I, 1 to n, yi minus, so the scalar product between A transpose sigma of W0 x I squared. So no lambda, no regularization. I just take the vanilla least squares problem on the neural network with fixed features, and I run gradient descent. So do you know what happens? If gradient descent is a deterministic algorithm. You start from some point, you run it, you end in a point. So you end somewhere here, right? In this regime when p is larger than n. If I just run gradient descent from zero initialization, so I initialize at zero and I run gradient descent, which solution do I get? Do you know it? Okay, So it's not a hard computation because this problem is quadratic, but you can do it because the gradient descent, so the gradient is linear, and then it's just an iteration, then you can actually write down the solution. And it turns out that if you write the solution, you get the blue dot. And that's why it's in the boundary, drawing the boundary. Because you are starting at 0 and then you hit the first point to get into the lake from 0. But okay, it's a picture, huh? 0 could be here, I don't know. I'm not putting where 0 is here. But this is a very important lesson, right? If we are optimizing a problem, which is over-parameterized, meaning that there are many interpolators, there's a manifold of interpolators. Here is a lake, but it could be like something more complicated. And we choose an algorithm. This algorithm is going to converge to one solution in this lake. And this solution might have some implicit property that depends on the choice of architecture of the network. And this is a bias, is what we call implicit bias. And this might be good for generalization. So one of the major questions in machine learning nowadays is pick your architecture, let's say a transformer. Do gradient descent. What kind of properties do you get in the solution, right? Among all possible solutions that the transformer could reach, one configuration of weights is going to be reached by the algorithm. What are the implicit bias of gradient descent for the transformer architecture? So we don't know the answer to this question. We know in very simple problems like this one, and they teach us some important lessons that we should think about implicit bias of optimization, but we don't know in general. So even a two-layer neural network where you train both A and W, we know a little bit about the implicit bias, but we don't know a full characterization like here.
Does this depend on the choice of the data that you use?
The implicit bias?
The more you get.
Yes, because the loss landscape depends on the data. So the loss landscape, so whether you're taking the finite n or n equals to infinity, let's think about the n equals to infinity. This is an expectation of the data distribution. So it depends on structurally on the data distribution.
So what will be the lesson for the practical point of view? So running different algorithms or?
So I think there are several lessons. The one is that running different algorithms can have different properties like the solution. So your network might lead to different properties. And moreover, in real life, this is also non-convex. So these different properties can be associated to different minima, but can also be associated to different minima on the same basin of attraction. So these two things get mixed up, and one should be mindful about the choice of algorithm. Yeah?
Is it important also to be mindful about the choice of the regularization? There are several types of things that here we use the quadratic one, but there's also another one. But you show that there are several.
Sure.
So those depends on the regularization.
So it does depend. So the loss landscape again depends on the regularization. But one thing that I should say is that here in this picture, I'm just using the regularization as a tool to pick up one solution. So I put this square regularization and then I took to 0, and this limit picked me one solution. And then I want to connect this solution to algorithm because the algorithm doesn't see the regularization. There's no regularization here. That's what is the subtle point, is that in real life, sometimes we regularize, but sometimes we don't regularize. And it's still the algorithm, regularization typically is there to help convexifying the problem by choosing something which, like say, it's confining or something that imposes some property. So regularization is what we would call an explicit bias or an explicit regularization. This that I'm just describing now is an implicit bias or an implicit regularization because I chose the algorithm and the algorithm chose to me that this solution is equal to plus lambda norm square and then lambda going to 0. So yeah, it's something that it's kind of obvious once we know it, but it took some time for the community, I think, to appreciate that one needs to consider different biases. There's the bias from the data that, the way I sample the data. There is the bias, the architecture, which we introduced last time. It's called an inductive bias, which is the hypothesis that you choose, the subset of functions you are fitting. And then there is the bias of the algorithm you choose. And these three things are there. Like you cannot hope to get rid of them. Like, it's a bit of a wishful thinking to say that I'm going to develop a theory of learning for any algorithm, for any data set, because these things have strong implications on the structural, like, properties of generalization. Of course, if your data distribution is generated by a teacher function that has some large norm, maybe imposing something like low norm is not good. So also the bias that the algorithm chooses might be good or not for generalization. This depends on the task, on the data. And by the way, if I have chosen here to add a lambda plus lambda, the L1 norm of A, when I take lambda to 0, I would get another solution here that is the lowest L1 norm solution. And which one generalizes better? Well, it depends on the task. If the task has some sparsity on the underlying structure, this is probably better. And if it is like dense but low norm, this is probably better, what we were doing. And by the way, if you're interested in that in this discussion, so here is a very simple model, but there is a small twist of this model we can consider that is a bit richer. It's called diagonal neural networks, which you can fully analyze the dynamics, and we can precisely see how the implicit bias of the solution depends on the algorithm that you choose. So you can have two different algorithms that give two different structurally different things. So it's something that I do in the course that I teach in the masters. And if you want, there are lecture notes for that, for analyzing the dynamics. Okay, so maybe I should, yeah.
Why being in the center of the space of interpolators makes
So I mean, again, I'm sorry for the picture. It's like the picture, there is no geometrical meaning in this picture. The only information I want to convey is that if you take another solution, there is one that overfits. So I'm not saying that all other solutions overfit, and I'm not saying that the position is important. I'm saying that there are many solutions. Some of them overfit, some of them not. And the one that we picked has this property that benignly overfits. Yes. So, by the way, we can also, so here I did this in one case, but we can actually understand quite well in this type of linear problems, what are the properties of this feature matrix here that lead to this type of behavior. So there is a very nice paper by Peter Bartlett, who is a statistician, who considered the question, now consider this to be something else, like just a Gaussian variable with a certain covariance, okay, some other structure. In our case, it is a Gaussian variable effectively because of Gaussian universality and has a specific covariance structure given by these weights. But imagine now you put any covariance and you ask the question, which covariances lead to this type of behavior and which covariances do not? So if you take isotropic data, you overfit. You don't get this behavior. The best error is below, is for p going to infinity. And essentially there is, just to give you an intuition about overfitting benignly, is that whenever your data is high dimensional, but your signal is effectively low dimensional, and your predictor, which is high dimensional, has some space to allocate to fit the signal and some space left to distribute the noise. So the key property is that the signal should be effectively low dimension so that you can place the signal into a small portion of the predictor. And then all the rest of the predictor can be used to dilute the noise such that every part of the noise into the entry of this vector should be small. And if you want a mental picture, so it's a sketch, but if you want a mental picture of what is going on here, is the following. So I plot to you what bad overfitting looks like. It's like these oscillatory functions that pick the noise. So how does benign overfitting looks like? So let's imagine that we have a true function that we want to fit. That's my teacher. It's like a sinusoidal thing. And then you have your data. So your data is this plus noise. And then you have your predictor, which the predictor should overfit, but it should not have large L2 norm. So it should not like oscillate a lot, because these oscillations, you pay a price in L2 norm, right? Because you go very far away, and the L2 norm is essentially the distance to the target. So benign overfitting is something that looks like this. So it's a function that, you know, stays close to the target and then spikes at the noise. So these spikes have very low L2 norm. You don't pay an error when you spike. So that the error is controlled by staying close to the. Of course, this is a picture in 2D, but this is a high dimensional phenomenon, right? So just a visualization. So this is how benign overfitting looks like. And the way you should think it is that the predictor A hat, the solution, lambda goes to 0, should essentially have a small piece that is the signal. And then you can distribute the noise in the other dimension. So the signal is actually in, let's say, RD. And here is RP minus D. And so you should enough space to dilute the noise such that you don't pay a large L2 price while you still pick the signal. So it depends on the geometry of the data, right? Benign overfitting depending on the geometry of the data. It's not something that could be captured by just like some bound that ignores the underlying geometry. So this is a lesson which is, I find is very interesting because statisticians, you know, statistics is an old field, right? Like least squares dates back to Gauss. And people for all this time believed that the bias variance trade-off was a fundamental thing, was kind of a theorem, but it's not a theorem, it's a folklore about this trade-off between complexity and risk. And then by looking at neural networks, we understand something about linear regression that people haven't understood before. So it's quite a nice nice thing. We understood something very fundamental about linear regression by looking at neural networks. So what is the takeaway? So the takeaway is that overparameterization is not at odds with generalization. Benign overfitting can be understood from simple linear model, right? And we have a discussion of implicit bias of algorithms. By the way, maybe let me just say one more thing about this is that I didn't discuss the logistic regression example. I just discussed the least squares because it's very intuitive to connect the landscape to the solution of a linear system of equations. But do you have any guess of what is the implicit bias of a logistic regression? So the implicit bias of a ridge regression with gradient descent was least L2 solution. Now let's say we do logistic regression, we run gradient descent and we wait until convergence. What solution do we get in the interpolation manifold? By the way, this lake is called interpolation manifold. It's the space of interpolators. Any guess? So it's a harder problem. You cannot do it in the board in half an hour. So essentially, logistic regression is part of a class of models that is called margin-based methods. So they are fitting a linear prediction for classification, and they penalize based on the margin, the distance to the margin. So you have like a linear method, and then you have the points here, and then the distance to the margin. So if you run gradient descent, you converge to the solution that has maximal margin, which is also called a support vector machine. So just a random comment. This was shown in a paper in 2017, so it's something very recent. Even though it's a convex problem for a simple algorithm, this was not known. Yeah.
This might be naive, but you showed this example of unique overfitting, and I'm having troubles to imagine how to achieve precisely a result like this with a few data. And I mean, how is that you're really gonna, with just this data, you're gonna really get the function without the noise? I mean, have you seen something like this?
So you want to do a plot, this plot?
Yeah, I mean, if you really have seen something like this.
No. You cannot see something like this because so this is a 2D plot of something which is p. So here is what? Here is x and here is y, right? But x is high dimensional, right?
That I understood, but what I'm puzzled about is that you really got the real one, just separated by the data. So I was just wondering if you can really get something like this. You know, my problem is that when you're not in the data, you're really on the function.
Well, I mean,
And
So-
so I was just wondering because I'm new to this field. I mean,
Sure, but let's look at the generalization error. So the generalization error is a R of A. It's the expectation over the data. Actually, let's not look at it. Okay, let me do it in detail. So y minus A transpose sigma of W0. And so here is for a new X and Y, right? So this is a just a transpose X and square, right? So, okay, so let's assume that y equals to some f star of x plus some noise, which has a finite variance. So what you can write here is that essentially what is the generalization error for this loss function? Is essentially sigma. Let's say that this guy has a variance sigma square, so expectation of epsilon square is equals to sigma square. So this is equals to sigma square, because I'm assuming also is independent from x, plus the L2 norm between f star and my predictor. So this is the predictor, right? That's f, let me call it f of hat of x, minus f hat on the L2 space with respect to the measure of the data, the marginal of x, no? So essentially generalizing well means to have this zero, right? Being close geometrically in this geometry to this. So if I have a plot like this, that let's say that the generalization error is going to 0 as p gets large, it must imply the f is close to this in L2 norm. But it's still you are interpolating, so you're picking all the noise. So the only way you can be doing this is that you are close to the real function in this geometry, and this picking the noise doesn't have a cost in this geometry. So you need to have these spikes which pay low price in L2.
This meaning is that the density of your data is not captured the curvature of the function.
Yeah, that's what the idea. But I understand now the logic behind it, and it should look like that.
It needs to look, if you have a plot that goes to 0, but I'm not saying that at finite n and p, like you are here, you have something like this. No, you are deviating a little bit of this, and the deviation should sum up to the right, like each amount that you deviate, it should sum up to the error in total. But in order to pick up the noise, I think the important part is that in order to pick up the noise, you need to be spiking, because otherwise it would be overfitting, which is the case when you are actually like doing polynomial fit on some random data in dimension 2, and you take the degree of the polynomial very high, you get these huge oscillations, and indeed what you're going to get is a U curve, and then boom, like overfitting, like not overfitting, bad overfitting or malign overfitting. I don't know if it's pronouncing it correctly, but yeah.
Those peaks makes the function. How do you do that with functions that are? How do you construct a non-differentiable function with something that is differentiable?
So why does it need to be differentiable?
The activation functions, I don't know.
No, I didn't say anything about the activation function. It could be like something like a ReLU that it has a point. So you are right that it needs to be regular, but it needs to be regular with respect to the expectation of the Gaussian measure here in this case. So the expectation needs to be like giving something regular, but the function itself doesn't need to be regular. Okay, so that's good. A lot of questions and discussion. Okay, so yeah, if you're interested in that, again, like, I have some lecture notes in, so I give a course which is for not for physicists, for like machine learning theory, people coming from computer science and so on. And if you are curious about that, like I discuss in mathematical detail, like when do you get these, when you don't get these is a function of the geometry of the data and so on. So you can take a look at these lecture notes. I think it's lecture 6 or something. Using just random matrix theory, no replicas, no physics. Okay, so this brings me to the last part I want to discuss today, which is about feature learning. So I didn't want to leave you just with the kind of convex linear problem. Actually, this brings us a bit more closer to nowadays, like results in 2023, 24. I would like to discuss them now, although I could have gone more into the phenomenology of that. Okay, so the first thing I want to comment to you, it's something about the limitations of this method, okay? So Gaussian universality is great because Gaussian universality allows you to use replicas and get these curves and get this risk, and it's nice. We are happy. However, there is something which is very disturbing about universality, okay? If I write down the risk, so exactly what I wrote down there, and I apply Gaussian universality, that I linearize this to first order, my features are linear, right? They are linear. So means that my hypothesis, my neural network, is only doing linear fit. Like it cannot pick anything more complicated than linear fit, which means that it's limited in expressivity. So even though it's a nonlinear function, even though it's a true linear network, because of universality, this true linear network is effectively like a linear method. And actually, you can see these, right? I mean, maybe I can sketch this argument. Is that so? You guys know quantum mechanics, so that's going to be easier to sketch than from people in learning theory. But so in quantum mechanics, we know that we can decompose Hilbert spaces in orthogonal bases. No. So here the measure is Gaussian. So the orthogonal bases are these Hermite polynomials. So let's consider a generic function f star from Rd to R. And this function is a function that is square integrable, so that this is finite, right? In L2 of the Gaussian measure. So my notation here was this was the joint distribution of the data. This is the marginal distribution. Okay, this space we know how to decompose it. So this space L2 of rho of x can be decomposed as a direct sum into different shells or sectors from 0 to infinity of some linear subspaces which are spanned by Hermite tensors of order m. So this is essentially the span. Essentially, let me write the decomposition of the function so that maybe it's more clear. So this function can be decomposed into some from m to 0 to infinity of, I have take like some multi-indices that sum to m of some coefficients of beta, the Hermite tensor of order beta of x. So what is the Hermite tensor of, so first so beta is a multi-index, so beta is equals to beta 1, beta d, right? So these are numbers, positive integers, and h beta is just the product of the Hermite polynomials he beta I of xi, I from 1 to d. So this is like just spherical harmonics but for Gaussian, okay? So you're just like when you're doing the hydrogen atom, you decompose into different spherical harmonics, right? So this is for the equivalent for Gaussian, like it would be the Hermite tensors. So each sector spans a space which are the space of polynomials of degree m. So the dimension of the space the dimension of this subspace, it's something like the combinatorial factor is the number of polynomials of degree m in D that you can take. It's a combinatorial factor, but when D is large, this is essentially of order D to the m. Okay, so there are more or less D to the m polynomials of degree D of degree m in RD. So if I want, so this is the target function. This is what I want to fit. So if I want to fit the component of the target function, which is of degree 5, right? I need my features to be at least a polynomial of degree 5. But because of Gaussian universality, I need to go to frequency, which is big enough such that degree 5 is finite, which essentially I need data which is d to the power 5. So this type of expansion in an orthogonal basis and this type of universality results implies that I can, with linearly much data, I can only fit a linear function. With quadratic data, I can fit a quadratic function. With cubic data, I can fit a cubic function. And everything else looks like noise because of the orthogonality in L2. So what I want to say, let me state it in a theorem, and this theorem was proven by Song Mei, Theodor Misiakiewicz, and Andrea Montanari in 2022. If you look at the paper, it's not stated in this way, but I'm motivating in this, like, more in a heuristic way that I think speaks to, if you know, like quantum mechanics, is that if you have isotropic data, meaning like spherical, Gaussian, in the hypercube, anything that is isotropic, the important thing is isotropic, and you have data, and the rank of this matrix, the feature matrix, which is the minimum between n and p, is d to the k, the best thing you can do in generalization is to fit a polynomial of degree k. So let me repeat this, is that we have the feature matrix. So the feature matrix phi is a matrix in R n times p, which has elements ik equals to sigma of wk transpose xi. So this matrix, the rank of this matrix is the minimum between n and p with high probability, because this is Gaussian, so it's full rank with high probability, but the rank is the minimum between n and p. So the bottleneck in the learning is going to be that I need the rank to be at least spanning polynomials of degree k to be able to learn the part of degree k because of this decomposition. And this decomposition holds because of isotropy. All polynomials are equal from the point of view of the Gaussian measure. So this implies this, this lower bound straight away. Questions about that? Is the hand-wavy explanation convincing? To prove this is hard because you need to prove the concentration of this matrix is a random matrix theory problem. In the polynomial regime, you need to prove concentration and everything, so it's hard to prove. But the idea is there. So what I want to highlight here is that whenever you have some sort of universality on your features are effectively equals to something, like you linearize it, this is going to imply a bottleneck on the performance. And in this plot, this line, this red line that was here, which is the asymptotic value when p goes to infinity, is non-zero. And what is this value? This value is the non-linear part of the function. Because effectively, since my features are linear, I can only fit the linear part, and the non-linear part of the function just behave as noise. So I have an effective noise, and that's where the method goes. It doesn't go to zero error. To go to zero error, I need to have p and n that goes to infinity at a polynomial scaling. So the plot corresponding to this result would be something like goes here, then goes down, eventually goes to zero, and this would be something like log, let's say, p of log d, and here would be the log of of the risk, or no, just the risk. And each of these sectors are kind of that you learn are kind of, one, this the two, and you learn sequentially the polynomials of higher and higher degree. And so this brings us to the fundamental question, which is, this method doesn't adapt, doesn't train the first layer, and we understand what are the limitations. So we understand that a non-adaptive method on isotropic data can only do polynomial fitting. So if we train the first layer, can we do better? Can we go beyond this in the proportional regime? Let's say we fix n and p equals to d, proportional to d. Can we go below this line if we actually train the first layer? If we achieve this, we prove the benefits of adaptation, which is one of the important questions. Like if you adapt to the data, do you do better than if you don't adapt? And you see that why the question is hard, because this method can fit anything as long as you have enough data and parameters. So the question of adaptativity is not trivial, right? Like even if you don't adapt, you can fit everything. So the question of the benefit of adaptation, it's fundamentally a question in statistics. You need to say, for a fixed amount of data, if I train, I do better or not than if I don't train? It's a statistical question. It's not an approximation question. So let's go this direction. Okay. Again, we like simple things. So let's start training the first layer. But if we really want to train both layers together, we need Fred and Leticia. We will need out of equilibrium dynamics in a non-convex landscape. It's hard. You need to write DMFT for this problem. Once you write DMFT, it's not the end of the game. You need to analyze DMFT and you need to prove what happens, right? So it's challenging. There are some recent progress by Andrea Montanari and Pier Francesco Urbani in this direction for the two-layer neural network, but it's not the simplest thing to do. So here we are humble. We are saying, okay, we are not going to go to the dynamics because dynamics is hard. We could, but we are not going. We're going to say, let's train for a few steps. We take 2 steps, 3 steps of gradient descent on the first layer, and then we stop. And then we fit the second layer. Okay, so effectively what we're doing is that we're saying, let's take this, train this for 1 step, and then fit the second layer perfectly. Now, in 1 step, if this step is large enough, I will be able to now have something here that correlates with X. So Gaussian universality is going to break down. And the question is, by breaking this Gaussian universality, can I prove that I do better than if I didn't train? So that's the question we are looking now. So there are two aspects to this question. So the first aspect is, if I train, do I correlate with the underlying structure of the data? Right? I do some gradient steps, my weights adapt. What correlations do I pick in the data? So remember that we assume that the data has this multi-index structure, right? So there are a few directions which are important. If I do this gradient step, do I correlate with this direction? So does the correlation with the underlying geometrical directions go to 0 or stay finite when the limit, I take the limit? So this is like about subspace recovery is the first question. The second question is, once I know that I align with some direction, how does this translate to the generalization error? So there are 2 steps here in this analysis. The first one is just trying to understand what do I correlate with, and the second step is, once I correlate, do I generalize better in this direction? By the way, I forgot to mention, like in the other method, notice that in this result, the structure of F star didn't play any role. And this is because the method is non-adaptative. So this assumption that this is a multi-index function doesn't play any role in this discussion, okay? And this is because the method is non-adaptative. So to correlate with this multi-index, it doesn't matter if there is a multi-index or not. Like from the perspective of the features, data is isotropic, everything is equal in RD. So the assumption on the data didn't play any role in this discussion. Okay. So again, the idea here will be to expand the nonlinear part of the target, F star, into some orthogonal decomposition. So F star is given by G of the projections along directions, R directions. So I can now expand this guy into the basis orthogonal with respect to this direction. So there's going to be a linear part, a quadratic part, and so on, just like we did in the board. And I claim that when you do gradient descent, what you correlate with is the lowest frequency part in this expansion. So the gradient descent is going to be correlating with the factors of the target function, which are dominating this expansion. So this is what is called the leap index of the function, of the nonlinear function. So let's take a look, just some examples. So if I have the linear function, the leap is 1 because I have the first non-zero part when I ignore the constant part is the linear part. So the leap of the linear function is 1. If I had a quadratic function, the leap of the quadratic function starts in the quadratic part. So the leap is 2. So if I have now a function which is nonlinear, has all the components, like tan h. Well, tan h has the first one, which is non-zero. You can expand and you can check that the first one is non-zero. So the leap of tan h is also 1. Like something like a product of 2 directions. The leap is 2, is a polynomial of degree 2. So the first term in this expansion is 2, is the second one. And if you have a product of r directions, then the leap is r. So I claim that essentially, after one step of gradient descent, your weights, your W, correlate with the subspace of lowest leap of the function. So if you have this function, you correlate with you recover the direction if it is linear. If it is a quadratic function, you need some data which is large enough to be able to correlate to the second part. So you need more data. If it is something nonlinear but has a low leap, you learn with n equals to d, and so on. So let's look at this plot. This phase diagram essentially quantifies that. So here I have the quantity of data in my gradient step. So n is the batch size on the gradient step. I'm just doing one step, okay? And here I have d data, d squared data, d cubed data, up to d to the power L. And here I have the leap of the function. So with less than d data, I never managed to correlate with anything. So I need at least d data to be able to correlate with one of these important directions. Then if I have d data, if the function has a leap 1, I correlate with the linear subspace. What is the linear subspace? Is this subspace. The subspace is spanned by these directions. So for example, if I have a tan h activation and I do one step, I correlate with this part and I don't correlate with the rest. Now I could have a function of leap 2. So with d data at leap 2, I don't correlate with anything. So I'm here, the red part. I'm not learning anything. So for a degree 2 polynomial, I need at least d squared data to correlate with the second order space, and so on. So the more data you have, with more directions you correlate, and the number of directions that you correlate at a certain sample complexity is proportional to the leap of the function. So that's the message. By the way, maybe I should just note in the board that, let me erase this, that this notation Z, so just to remind you, f of x is equals to g of W1 star transpose x, W2 star transpose x, up to WR star transpose x. So let's define ZK equals to WK star transpose x. So the pre-activations, such that essentially as a function of Z, I have like the target function f star of x is equals to G of Z1 ZR. And then I do the decomposition of this function in the orthogonal basis. And let's take a very concrete example. Let's say I have a leap one function. So a leap one function, after one gradient step, what do I learn? I learn the sum of all the first order functions. So if n is proportional to d, and I have my gradient step, like theta hat after one gradient step, is going to live in the span of this linear subspace, which is the sum over k of I from 1 to d, no, sorry, for 1 k from 1 to r of some coefficients. How do I call the coefficients? Mu1 k, w star k. So this is a linear subspace. So if you have a leap one function, you correlate with a linear subspace. Which subspace it is? The space is spun by the sum of the directions. So I learn the average direction weighted by the coefficients, to be a bit more concrete. And then the question is, if I do this step and I correlate with a given subspace, do I generalize or not better? And so what we can show, and so here I'm stating like as a theorem, and this should be compared to the other theorem, that the risk that you make after one step and training the second layer is going to be lower bounded by the variance of the target function, so the variance of this function you want to learn, conditionally on what you learn, on the subspace that you learn. So essentially, this is telling you that at best, after one step, if you correlate with a space, you can learn all nonlinear functions in this subspace. And then the error is going to be everything else that is orthogonal to this subspace. So let me be a bit concrete about that. Like, let's look at like the proportional regime. Is that if I now have n and p proportional to d, I can learn any nonlinear function of this subspace. So if I have a leap one function and I correlate with this average direction, after one step, I train the second layer, I can potentially learn any nonlinear function across this along this direction. Now, the math is kind of heavy to write because you need to define this in an invariant way, this expansion, but that's the intuition, is that your weights after one step correlate with one direction, and in this direction, now you can learn any nonlinear function of this direction. So let me maybe give a picture that is a bit more informative. Is that at initialization, my weights were random. So this is like, let's say that is a spectral density of W. So at initialization, I have random weights. So I have Gaussian universality. So my spectrum is essentially a shifted Marchenko-Pastur. It's something like that at initialization. Then I do one step. What happens? So if my target function has leap one, and I have enough data, I have n proportional to d, what happens is that I get a spike that pops out here. And this spike, let me call it v. So it's a function in where? Rd. And what it is this, the sum of all these things. And what is crucial is that v, the scalar product between v and w star k, is bounded away from 0 in the limit. So you have a positive correlation with the direction. And you can actually quantify exactly because you know what v is, right? But you can see the feature learning as a spectral transition in the like a BBB transition in the spectrum. So if you were hearing the talk that I gave yesterday, this is exactly what you used, but in this kind of hierarchical task where you have like a sequence of transitions and you learn them progressively. But this is the baby version of what I told you yesterday, is that we can see like the learning of the features as the progressive like spectral transitions of spikes which correlate to the data, and then the part which is left behind, the bulk, is effectively like noise, is the part of the weights which are still random features. They are still like isotropic everywhere. And so the price that you pay in generalization along this direction goes down drastically. You can learn any nonlinear function of this direction. But what about the other directions? Well, random features. For the perspective of the other directions, you're just doing random features. So what do you pay to learn, let's say, a direction orthogonal to V? Well, to learn a polynomial of degree kappa or k of this direction orthogonal to V, you need d to the kappa. While to learn a polynomial of degree k of this direction, you just need n equals to d. So you go from d to the k to d in the direction that you correlate. Is this clear? Cool. Moreover, let me tell you a second fact, which is a bit more involved, is that all that I have told you so far is essentially concentration of random variables. So you can prove these results by just computing expectation functions, okay, and limits of expectation functions. Now we as physicists, we like exact asymptotics. We like exact results. We are not happy about just having like, some lower bound, right? So like an equality here. What is the error equals to in the regime? So it turns out with this picture, you can derive also asymptotics. But remember, how do you derive asymptotics? You need first to linearize your features and then get some Gaussianity and do replicas on Gaussian variables, right? Because we don't know how to do replicas in non-Gaussian variables. So we need to connect back to Gaussian. So we need some sort of a Gaussian universality for this type of features, right? So let me write in the board again. So what are my features? My features are, so again, ik is equals to sigma of wk, right? That's my weights, transpose xi. But wk now is after one step. So after one step, I claim wk is essentially equals to wk0 at initialization plus some u times v, some uk times v, where v is this spike. And actually this is not equal, this is approximately, and the quality is in the limit, okay? Okay, so now what do I need to do? I need to compute what happens like now for this model. 0, sorry, transpose x plus uk of v transpose x, xi. So what is this? So before, by Gaussian universality, this was just a Gaussian variable and you could expand. But now life is hard because you see, this is still like a Wishart-like object. This is the part that correlates with the bulk. But now there is this spike, and I have a nonlinear function of a Wishart type matrix plus a spike. And this is tricky, right? I mean, if you have worked on random matrix theory, like, computing like the spectral density of a matrix of this type, let's say phi equals to something like nonlinear function of x w0 transpose plus u x, I think, transpose v. So x is n times d. So yeah, something like that. That's a very non-standard random matrix theory problem, and that's hard. It's hard to compute the spectral density of that. So the spectral density of what is inside is clear, but now after you pass through a nonlinear function, so this in order to do exact asymptotics, I need to deal with matrices of this type. It can be done. So the idea is to do something called conditional Gaussian equivalence. So the idea is that we condition on the spike. So conditionally on the spike, we do the expansion with respect to the Gaussian part. And then we get some sort of Hermite decomposition, n from 0 to infinity, of some coefficients, m. But these coefficients are going to depend on the spike. Some sort of like x times v times the Hermite part, which depends on this, something like w x w0. And so this is conditionally like what's called CGET. And then this allows us to do replicas on the top of this decomposition. And then you need to deal with the fact that in the end, you need to deal with this expectation of the part you condition after. But okay, it can be done. The computation is horrible, but you can get this type of plots. So let me go through the plot. So generalization error against alpha. Alpha is n over d, and I'm in the proportional regime. So if I have I have two alphas now. I have the alpha of the training of the second layer and alpha of the training of the first layer. So alpha of the training of the first layer is here, alpha 0. And this is the alpha of the training of the second layer. So if alpha 0 is equals to 0, means that I didn't train at all, right? I don't have any data in the first layer. So I have just random features. So random features is here, is the curve that we saw before. As I start training the first layer, I start getting something that gets better and better. And this line here is the best linear approximation of the target function. So what I'm getting here is that as I do feature learning and as I increase alpha, I start to go below this line. So this is essentially a visual picture of this theorem. And this also allows us to do some very nice things. So for example, we can control perfectly what type of approximations we are learning after doing this one step. Because if we have this Gaussian equivalence, conditional Gaussian equivalence, we effectively understand how the features look like in the limit. So we can understand what is kind of the adapted basis that we are getting. And here I'm plotting, like here's the true function, the target function in dotted. And so here are like two like representations. So there's a lower and upper bound that you can get from the formulas that sees like this is like this is how the features are learning this nonlinearity. So I can bound it from below and from above by the orange and blue curve. So here you get like an effective picture of what is the basis that you are learning that allows us to break this isotropy and therefore to learn better than the weights at initialization, better than the random features model. And I should also comment that there has been works done about perturbative corrections to random features. So these are 1 over p corrections. And all of these cannot be seen in these perturbative corrections. Actually, for getting a result like that, you really need to have a non-perturbative description of this transition. Because in perturbation theory, you never see this spike out of this bulk. So you really need to have an understanding of the control the non-Gaussian part of what is being learned. To first order, everything remains Gaussian. So are there questions? Yeah.
So you mentioned the data, right?
Yeah.
So your practice in SGD, the batch size, everything mentioned the data is what?
So this depends, I think, on the problem. So, you know, if you're doing training a large language model is like billions of tokens, the quantity of the data, and typically you take a batch size, which I think, you know, maybe thousands or 10,000. So very different. But notice here I'm not doing SGD. So here I'm doing one step of GD. I'm doing over the full batch of data. And by the way, I'm assuming something very important, which is that, okay, maybe, okay, let me explain why I said SGD. So I'm assuming that between the first step and the training of the second layer, I'm taking fresh batches of data. So this reduces the correlation and makes the calculation easier. if you start like now taking the same data that you train the first layer and you train the second layer, the problem becomes much harder. So that's why I said SGD, because some in learning theory, when you say SGD, sometimes we refer to the fact that at every step you have independent batches. Online, yeah, exactly. Or one pass, sometimes people call as well. So this simplifies life. But yeah, it's an interesting question when you use the same data. It becomes harder. Nevertheless, notice that even though you are uncorrelated on the batch on the first step and the second step, you still have the correlation because the data, the function, the teacher is the same. So the target function is the same. So the W star is the same. And that's why you inherit correlation between the two steps. But the correlation is not through X and it's through Y. So dealing with the both correlations is an interesting question. But we did some simulations and we didn't see major differences in the phenomenology, but the curves look different. Okay, so maybe I can summarize with what we discussed for one step. So after one step of SGD, first layer weights correlate with the relevant directions of the target. So if you have proportionally much data, you learn an average direction of all the indices, a weighted average direction, where the weight is the coefficient of their Hermite decomposition across this direction. If you want to learn more than one direction, well, you need at least this square data. So you cannot capture this learning multiple directions with just the proportional regime. And the quantity that you need exactly depends on the leap exponent of the function. And this leads to a natural next question, which I'm also just going to give you a little bit of the results to you, which is what happens when you do multiple steps? And always I'm going to be thinking about multiple steps with independent data at every step to simplify my life. So essentially what you get is what we call a staircase phenomena, is that as you do more steps, you can learn more directions if you fix the number of data, as long as these directions are correlated in a particular way. So let me just give you some intuition, because to actually describe this mathematically is not straightforward, but the intuition should be just that if you do more steps, you might learn more, but you only learn more if the directions that you learn at the first step is correlated with the second one and the third one in a particular way. And let me describe what this means. So informally, if they are linearly coupled, you can learn in a sequence as in a staircase. So let me give you examples. I think it's better to give examples than to try to formalize exactly on the board. Let's have a target function which has this shape. So g of z is z1 plus a function of z1 times z2 plus a function of z2 times z3. So for this function, which has this special staircase structure where there is one linear part, and then the first nonlinear part is coupled to the linear part in a linear way, and the third direction is coupled with the second one in a linear way. At every step, I manage to climb this nonlinearity, even if I have just proportional data. So I learn first Z1 in the first direction. In the second direction, I learn Z2. In the third step, I learn Z3, and I can climb one by one. So 0 steps, 0 directions. T equals to 1, I learn the linear part. T equals to 2, I learn the quadratic part. T equals to 3, I learn everything, because the function only has 3 directions. Let's take another example. So now I have something like Z1 plus GZ1, Z2 plus H of Z1, Z3. So now the Z3 is correlated with Z1, not with Z2. So I take one step, I learn Z1. Well, Z1 gives me access to both these two parts. So in the second step, I learn everything. So I just need 2 steps to learn all the 3 directions. Now let's look at something hard. I have Z1 plus G of Z1, Z2 squared. And G of Z2, Z3. Okay, so in the first step, I guess you guessed that you learned the first direction. But now the first direction allows me to climb to the second one But the second one is a quadratic direction. It's not linearly coupled. It's quadratically coupled with the first one. So I need d squared. But since I only have d data in this example, I cannot climb. So I get stuck. So t step 1, 2, 3, 4, 5. In actually to learn more, I would need to do d squared steps. So if I would do a DMFT analysis of that, I would also not be able to capture more than the linear part. So yeah, this is a harder function for SGD. And then let's say like a very hard function is a function that doesn't have a linear direction. I cannot learn anything by taking gradient steps with linearly much data. I need to have more data to be able to resolve these nonlinear parts. So okay, so that's the last thing I would like to tell you today. So let me summarize this. Takeaway number 4, with more than one step, you might learn linearly correlated subspaces. In particular, there are some models that have a structure such that you can learn all directions by taking several steps with just proportional data. Which functions are those? These are staircase functions. These functions that have this structure where linear part, like non-linear part is coupled to the linear part in a linear way, and then so on. Allows you to climb the staircase with the steps of gradient descent. So this defines functions which are easy for SGD versus functions which are hard for SGD. So open question. All of these that I told you here is about computing correlations of gradient at step t with the directions and taking expectations and then seeing if it is non-zero or zero when the limit goes to infinity. Can we get a picture like can you get an exact asymptotics picture like this for more directions? We don't know. Can we do random matrix theory on features after t steps? We don't know. So these are all directions which are open. So for example, drawing these very precise curves for step 3 of gradient descent for a staircase function, where in principle you can learn this part, and looking what is the adapted basis, how does it look like, what kind of approximation you get. These are all things that are doable, but are open. So yeah. So I think I will stop here for the interest of time. And I mean, I'm happy to have discussions about this in the time that we have for questions. And the only other thing that I had in the lectures that I didn't cover here that are in the notes are about like fundamental limitations. So all of this is for SGD, but you can ask from the perspective of the optimal method, like this AMP that I introduced in the first lecture. Is there a difference between the complexity of learning with the optimal algorithm versus learning with SGD? So is there a separation between SGD and AMP? And indeed there are. AMP defines a class of functions which is hard, which is different from the classes of functions which are hard for SGD. And this touches a little bit this question of implicit bias that I introduced in the linear model. But I guess this will be for next time. So I thank you for your attention, for sticking to the lecture until now, and happy to take questions.
This is kind of getting back to the question I asked, which is, so you're saying that in order to learn nonlinear features, you need amounts of data in a mini batch, which is powers of the dimension of the data. But like, for images or something, these dimensions are huge. Is in practice, do mini batches get this big, or is something else happening?
There is a fundamental difference between images and what we are doing here.
Sure.
Which is that images, like there is information on X. So you see like the data itself, X is correlated. It's not isotropic.
Yes, true.
So
okay.
here we are doing a major simplification, which is X is unstructured. So if you look at X, there's nothing to be learned from X.
Okay.
All the information is on Y given X. And it's already hard to do these things. But for me, the major fundamental question is that now what happens when X is correlated with Y? How does this picture look like, right? How much data do you need? as a function of this correlation. So
Yeah.
they're all questions that kind of are research questions. So I've been going to this direction, but we know very little about it.
Sure. But you feel it must be smaller, right? Because no one is using like
must, because
dimension of pixel space to the cubed for their images, mini batches.
So in real life, I think most of the time it's a case that is smaller.
Yeah.
But there are some examples which are called adversarial problems, right?
Yeah.
Where you poison the data such that it makes harder. So this is also interesting. There are some cases where you can also introduce correlations that make it harder to learn. So this is also like an interesting research question. Like, yeah, if I'm an adversary and I want to poison your X and give to you the X, can I make it harder to learn with SGD?
But then the intuition is the other way, yeah? When you have.
Yeah.
When you have correlations, then it should be easier to learn.
Yes.
I mean, unless there are the poison ones, but.
Sure, yeah. In the typical case,
Mhm.
like it should be easier. And I can tell you one result that we have about this. So we know what happens for this theorem. We know what this theorem looks like when X has a power law decay in the covariance. So X now is correlated with a covariance that has a power law decay. So this introduces an effective dimension. And then the complexity, guess what, is governed by the effective dimension. But we only know this for kernels, like for the initialization problem. We don't know after one step, like all these things are open.
Another question? No? Okay, now we have a coffee break, 30 minutes, and we go to the
Yeah.
conference.
I'll make sure to not bring this with me. Anybody on Zoom, this is the conversation.
I give a talk where my talk techniques at code, which I'm actually implementing sketching for two. So I can show you this. So getting the sign function is really possible. It's literally just, you get not exactly the picture, but here. This is weird system. The under of the graph. And then, okay, so let's say, here's the basis of the function. So here's the standard picture, right? Same number of parameters. So then here's the curve of these area. Machine learning is that here's the example of hitting what you did is this isn't actually bounded. So better than get something which is not so bad away. But it's kind of a lie, right? Because of course, you see, there's many ways of and this is one this is actually here's some bad ones. And the question, the thing is in linear least squares, it's proven that when you initialize from basic therefore it turns out it is not any problem. Quadratic factorization. Not that in fact, with a different basic function. This was on make the basic function. So this is more like a network same function shifts. Now, you do this and then you do the same thing. You don't have the huge like the second thing is you also can start getting better after interpretation.
Sorry. Because, you know, these are considered after interpolation, if your data is sparse and the noise is this is what the situation I had. Your data is actually in high dimension. Is actually not dense. And the noise that goes with it. Not like. Yes, and in this case, better after separation. Because the implicit bias gives you things like small prediction, right? So this is the bits of plus two of this points. Just starting from the low norm. It looks like it's getting the curve. It's just because the effective regularization is biasing small curvature solutions. You can see the most area do better after the. It's actually, they made a code to do all this. I can make a code. I think and I was talking about that. Okay, so yeah. So it's more than it doesn't exactly what we wrote. Yeah, with this, you'll never really get assigned to a lot of data.
But it was because the noise was so small, yeah? Because you're actually going to get around it slightly slow because you're, I mean, you're getting the curvatures and you cannot get precisely these spikes. It's true. No, I know, that was, but it should look like that. In the, when the error is just the sigma squared, then the other thing should be exactly the function.
The problem with this cartoon improvement is that it's very bad in your high dimensions, right? Do you think about the dimension of the space of image vectors is super massive, right? And honestly, in most circumstances, the amount of data you have, the order dimension, right? The dimension of like high quality images is like billions, right? And the number of images you have is also like billions.
Yes.
So when you think of any, oh yeah. So when you think of any projection, when you do have any projection in high dimensions along a given axis, you're only going to have near that axis one image. So this cartoon of having a lot of points that you're sort of interpolating the spikes, this isn't really right. We should think that like it's super sparse. It's fast. Yeah, exactly. Maybe just start talking about something like that. This is the you take the sign. Yeah, exactly. This is the ground truth function. And then fitting is this is linearly squares. So you have basis of functions. So here's the class statistics picture. You have the four little zipper there, just one spot. Then you say machine learning uses many more parameters. And here's the this is polynomial. You have to start from 0 to 1. Yeah. And you can see that you don't go better than you do at the nice balance. You still do a workshop. Yeah. And so here's my slide. I show different of the different fits, and then also different perfect fit parameters, right? And then the story is this. But then so this is you change the basis. Yeah.
Well, I mean, it's not too important.
I know, but the practice is not as long. Right? So the example is this is this polynomial basis. That's the value base. Take the value function shifted. Don't be done with it. Essentially, what I mean. And then the last part of the story was okay, more realistic comparison. It's not idiot, sparse data.
Ellos mandaron las presentaciones de los proyectos de acá,
Ah, ok.
o las proyectos de Gabriel.
Sí, yo iba a buscar la
Archivos de tu página.
Again, just doing gradient descent, starting from zero and one. Doing the absolute value of this. You start to get the curvature of the function.
¿Lo vas enseguida?
No,
Más tarde te...
tu sesión.
Sí, sí, sí. Por la tarde.
Pero solo quería ver si funcionaba todo.
Sí, ya puede costar, porque todavía no está completamente terminado. Voy a utilizar el tiempo del almuerzo.
Ah,
No en mucho, pero
pero es algo que ya has dado charla de eso.
sí, pero no era el mismo público, entonces quisiera hacer un poquito más suave. Y esto no me daba cuenta pues, que vinieran.
Claro, yo estoy igual porque te voy a hablar de quantum computing. Y pues este audiencia no es de, entonces va a ser muy
Sí,
broad scope.
sí, cuando lo propuse a Gabriel estaba preparándolo para la charla en Japón, en Kyoto, el mes pasado. Entonces dije, bueno, si te interesa. Pero no, en una conferencia de interactivo. Entonces la gente sabe de qué trata y aquí es un poco diferente.
Es muy diferente. ¿Cómo está? Hola.
Está bien, ¿cómo vamos? Bien, yo seguiría a las 10,
Pues sí, pues,
10:30.
¿Cómo tienes tu presentación?
Yo la mandé en PDF, pero yo tuve que usar unas animaciones. Entonces entrar a mi cuenta de Gmail si puede. No traje cómo porque no sabía si era fácil o...
Yo creo que yo intento desde acá entrar. Yo voy a buscar a Gabriel, casi que sabe la logística.
Bueno, vale. Gracias.
Hola, buenos días.
Hola,
Mucho
buenos
gusto.
días.
Alejandra Valencia.
Mucho gusto, Alfonso Leiva.
Según entiendo, voy a estar haciendo de chairwoman.
Ah,
Eso
excelente.
era solo como para
Conocer.
conocer.
Muy
Pero
bien.
y entiendo que usted ya sabe, no sé bien para proyectar.
No, yo la mandé en PDF, pero es que yo tengo un par de animaciones
Ajá.
y me gustaría
Ah,
usarlas. No usarlas.
¿El computador
Eh,
necesitas?
o aquí no se puede conectar eso.
Sí, profe. Yo, ayúdame. Pues, hay dudas. Se invitó el Zoom a otros para que ellos vengan para que le pongan Zoom o que descargue ahí la...
En este computador.
No, pero yo ya las mandé.
Ah, entonces esperemos a Gabriel, pero lo que quiero es proyectar de video dónde está ahorita.
Yo tengo mi presentación en mi cuenta de Gmail, porque en esas presentaciones tipo Gmail funcionan los videos.
Ah, listo.
En el PDF que normalmente uno hace, no funciona.
Ah, entonces debería funcionar con
Yo esperaría que
Ah,
sí.
listo. Entonces, ahí estás entrando en este computador. Ah, bien.
Sí, sí.
Ah, listo.
Alejandra Valencia.
Sí, de acá del lado de los Andes.
Mucho gusto.
Yo estaba buscando. No conozco.
No pasa nada. San Juan, mi familia, y un par de conocidos. La gran mayoría de las veces los estudiantes de mis clases ni se acuerdan del nombre del día del examen.
Ah, sí, exacto. Solo cuando van a pedir la nota y eso.
No, ni siquiera.
Usted trabaja dónde?
Yo trabajo en la Universidad Javeriana.
Ah, ok.
I don't know. I don't think so. Yeah.
Gabriel estaba no.
No, esto debería funcionar, ¿no?
Sí. Con suerte.
No, esto normalmente sirve. Sirve. Típicamente sirve.
Pero, listo.
Ahí, entonces lo que uno debe hacer, si no ha cambiado mucho la cosa, es compartir desde
La
Zoom
pantalla
la
desde
pantalla. que pongamos, no, esto es lo que toca compartir. Que ahora ya entiendo lo que sí, sí, listo, ya,
Y aquí en más le puedes dar para ocultar esto, que le puedes dar clic.
Ok,
Si lo quieres ocultar, no sé qué tanto espacio se le...
pues no sobra, ¿cierto?
Ahí está Hide Video Panel o Hide Floating, no sé qué. Algunos esos hide tienes que el de arriba.
Hay names on annotations, esto, floating meeting, listo, ya. Sí, esperemos que sí.
I don't know if they are, I'm sorry, what you're doing organizations, small children,
Por estas cosas que ayudan
A visualizar, ¿sabes?
a que la cosa sea menos enredada para mí. Listo, esto es lo que hay que mostrar en realidad.
Perfecto, gracias.
Teachers, all the things that you have. If you like, no, you're using some runoff. And then you try to learn those from the notes from the but you learn it. So many albums that are right. I'd say that it's you still love there's something I think it's like defining what are the supporting questions, because I think I don't appreciate those other things. It's like
It's a field that's trying to
No,
combine
ayer,
two things that are going really fast.
Yes. Semana
I have this.
no, más así, esto se debe hacer para leer bien.
There's a lot of trust. There's a lot of, I mean, not the ones that not a
Ya compré el libro. O sea, yo la próxima voy a digamos eso. ¿Cómo se pero sí, sabes que esa es una pero veo fuerzas igual y además cogen las fuerzas del cuerpo, igualan a la masa total de y yo ya me acho, yo me pongo
Yeah.
Yo sí. O sea, nos mantenemos a ellos. Y ellos son
Entonces, bueno, voy a aprender. Pues puede haber libros,
pero está por ahí, está por todos eso. Creo que ya el profesor hizo todo y para proyectarlo, porque lo quería hacer desde el que para su video.
Sí, porque no, está bien.
Las otras escritas voy a presentar.
Ya no está. Mira, el segundo entonces no la de que no está tan
Listo. La dejas ahí, esa carpeta está y el de John Freddy no la
Freddy no ha llegado. No sé, no me mandó, los que no mandaron no usan su computador. Pues ya tienen instrucciones de conectarse a su.
listo. No, está.
Hola. Hola, mucho gusto, ¿cómo vas? Alfonso le digo. Entonces, yo había enviado el PDF, ¿cierto? Pero entonces, como decía en el correo, yo uso parte de libros que ahorita yo que la funcione. Este es uno de los que trabaja, pero este no está aquí en Colombia, entonces yo lo que voy a hacer en la, ¿cómo se llama? En la, cuando uno hacía la agregar personas, eso te que estar inscritos en LinkedIn.
Sí,
O sea,
para poner el nombre a.
de alguna manera, sí. Pero sí, me gustaría que si sale algo, no es.
Listo, sí, yo lo puedo.
Sí. Si no, luego te va
Pues solo estaba el nombre del no.
en el abstract no se podía poner el nombre, porque tú subías el texto, el título, y los autores y todo eso venía en la
Pero
plataforma.
en el archivo que yo sí estaba.
En el de esta mañana, que esta mañana en la presentación sí está.
Bueno, pues yo
Lo único que le hice fue cambiar una diapositiva, cambiando la.
pues yo la actualizo para que lo de la
Tranquilo, yo llegué pensando que me iba a poner.
Y está profesor, o sea, acá, ¿cómo dónde está? Se dice que sodio, ¿cómo se pronuncia eso?
Yodo.
Pero y en inglés, ¿cómo?
Natrium yodado. Natrium
Natrium yodado.
yodado.
Solution spaces. The motivation was all this stuff to say, okay, we understand well how this works with linear regression, primitive linear regression. Non-linear regression, now your solution space, who knows what it looks like? Is it one piece? Is it many pieces?
Yeah,
That went into my talk.
that's also very. So. Interpretation.
Yeah, I mean, so this is, I mean, the canyon manifold model was originally introduced by Jan Leva. It's a model of nonlinear least squares, random nonlinear least squares.
No, sure, no, I'm saying that are interested in but like something like just but you wouldn't want to target that.
Yeah.
Like something distribution of values.
Yeah.
But it also some of the
No, this is why I've been trying to develop methods, right?
okay, so you want this action.
Yeah. So the work that I was, the work that this talk was eventually about was, I can confer for systems where, say the loss is analytic, right? Or sorry, so you don't have case like, the characterized case, like the Euler characteristic of the set of solutions of the interpolation. In expectation is it. No, it's the expected value of the Euler characteristic. So it's a topological characteristic. So in my case, it's this non-linear squares model, right? So the actual model is the sum of a bunch of pieces and all these zeros. But the method is very general. In principle, it's like I'm thinking to try to use it on like a tree committee machine. It's the easy first, right?
So I have one, so maybe something interesting. I have another one. What if you like take for instance, like, there are some works. Any sorts of solutions
Yeah, I've seen someone talked at one of the, you kind of mentioned studies.
Pues en una carrera.
There are these things. There are always so actually, the question is like, for some of these means, like the real idea, like it's a so I'm just I actually find some
I mean, I've been working on this in another direction. I talked about this in so the one thing I can do on these this kind of thing of computing problems in individual pieces, this is hard. Recently, just trying about this. It's a cat's life, where it's like calculation, where you count. Characterize categorized style statistics of sphere, but inserted into the solutions. You understand something about the geometry of the set based on like how many in the solution set, how many spheres of this radius can be inserted into the boundary. So this is something that is more in this direction, not exactly the same. But this thing of a volume is hard. I think volume is the same problem as you have for basic contraction, which is that you basically need to do some kind of asymptotic T. Because it's local.
Listo.
So instead of entrepreneurship,
Normally, if there's problems I've said so far, that the existence of problem takes the time.
Very recently, I got this, just.
I saw, yes. And I was like, there should be some more citations. I'll send you, I'll send it.
Because,
Okay, good morning, everyone. My name is Alejandra Valencia. I am a professor here in the physics department, and I will be doing chairwoman for this session. So, okay, so let's start with Professor Alfonso Leiva from Universidad Javeriana here in Bogota, and he is going to be talking to us about statistical mechanics, insights on
Natrium.
iodine, importer transport cycle. So, okay.
Okay, thank you very much for the kind introduction. Thank you, Senator, for inviting me. I have been told that I should put my slides in English, but I am free to speak either in Spanish, English, or let's do some average in German. French. Then, okay, entonces los muchachos jóvenes, ¿cómo estamos con el inglés? Bien. Los menores, los de 25 a 30 bien, y los menores de 25. Bueno, voy a empezar. Entonces, statistical mechanics is okay. Okay. It's a very important tool in physics, but beyond physics, for instance, in the field of biophysics, for molecular dynamic simulations, to get extra information in biosystems is a powerful tool. Actually, it's the most powerful tool up to date. Our application today is the thyroid. I don't know how to pronounce tiroides in English. Thyroid. Entonces, natrium iodide importer. Importer is actually is a channel. It's just a channel. Basically, it's located here. Here is the anatomy of the glandule, and here is the important part for us. Here is the cross section of the pieces, small piece of the gland, and here is our molecule. The molecule is actually pumping. Let's say so for now. It's pumping the ion of iodide from outside to inside, and some companionship of in order to get this happening is not right. Okay, this is important. I forgot to say that this gland is very important to keep the health. Either when you are a child, a newborn, and even a grown person is, I mean. And another goal here is in order to understand the transport of the iodide from outside to inside is cancer treatment also. Because cancer is treated with iodide 19. Okay. Part of this work has been already published a couple of years ago in this journal, Nature. And this is an upcoming paper. We submitted this paper last year. And also to Nature that we are waiting for to be published. We do a statistical mechanics for particles, yeah? And in order to do statistical mechanics with particles, we need to know the coordinates and eventually the velocities of each part. As in every book problem in physics, in standard physics. In order to get the coordinates of this little guy here, we need to perform some extra experiments to get the actual 3D atomic structure of the molecules. So that's the macromolecule, right? Once you get the structure, you are able to start to study actually the so-called mechanisms. Mechanisms means here every single macro state, conformational state in terms of the biochemistry of the problem. Let's put it this way, in the actual way. Yeah? In biochemistry, actually in organic chemistry, every process is driven by electrons, right? And in macromolecules, when you start to move electrons around, the macromolecules change actually the conformational forms. They do move. They do really move like big bodies. Each move of that corresponds to different statistical or thermodynamic states. And these states are very important for the intermediate states in the biochemics. Yeah? Then you get to find some molecule here, this guy changed this form. And when this guy changed this form, then the electrostatic, the thermodynamics, and the actual biological functions change. That's the key point here, right? Here you get some little pictures of what's going on. This is the important point right now. Here, what is important is to understand how the iodide goes across this macromolecule, right? That's the point. If you see with the mechanistic eyes, what you see some are tunnels. And these tunnels allow the transport of these ions. That's one part. If you see this problem as electrostatic surface, what you are obviously an actual electrostatics surface. Equipotentials eventually, of course, they are gradients. So then, to the physics, you need to get the Hamiltonian, yeah, and you solve the equation of motions. Here you need to do some computer calculations. You have the Newton law here, mass by acceleration equal to the force, and the force here is some heuristic force because of the complexity of the problem. This is one of the standard, I'm going to talk here in like 30 seconds. This is one of the standard potentials for biomolecules. You have actually, the real physics is here. You have here electrostatic and van der Waals. Electrostatic because of the charge, and van der Waals because of the screening of the Coulomb interaction. And here you have, in terms of the Hamiltonian or Lagrangian mechanics, you have yes multipliers. You have yes restrictions to move, and this restriction to move, for instance, here the distance is called in terms of the chemist a bond. The restriction to do the rotational movements are also called angles and diedrals and proper sums. These like 4 terms are meant to keep the architecture of the molecules. And you keep this architecture by introducing restrictions, multipliers, basically. Okay, and here is the actual physics. Of course, there are really a lot of different representations of these potentials because of the scale, because of the nature of the specific molecule, and etc. The set of this parameterization is called force field in the technical argot. So because of the complexity, not because of the physics, but more in terms of the dimension of the problem, we use this algorithm, normal given let publishing this date with and then you put everything in the computer, and this is more or less a standard protocol to perform molecular dynamics. You get the structure, and you need to do this called energy minimization. This energy minimization is because the coordinates that you get from the experiment, they are real coordinates. Actual coordinates because of the physics, in terms of the physics, the chemistry, and so on. But once you put here some parameterization, the restriction to move, to rotate, and so on, regardless of the how you obtain this coefficient, this distance, also, basically those are mostly quantum mechanical calculations and spectroscopically experiments. However, they are data most in equilibrium, and you need to get some dynamics. Then what happens here is that you need to reconcile this force field, which is some radio representation of the actual sign that is happening in there, with your representation of the force field. And also you are reducing a lot of degrees of freedom. And then you start to move the system with the Newton or Lagrangian or Hamilton equation of motion, depends. Once you get the system to move, you start to really to capture, to project the data that you are going to analyze to get the biophysics of this problem. Here, what we are really studying is how what was the molecule here? The iodide is coming from outside of the cell and going up to here and then up to here. Actually, the tunnel is like this. Normally, in the computer, to get the iodide to cross the whole molecule, you need to pull. You need to put an extra term in your force field to get this guy to cross the whole macromolecule. And then you study the energetics of the tunnel. You see here some parts of these little molecules here, some little parts in the of the amino acids, right? And for instance, if you do a little preliminary data of the crossing, you get this energy surface project to the reaction coordinate, the reaction coordinate. Thank you. And then you get that here. This is not really important for what we are going to show now. Then the actual setup of the simulation, here you have the molecule with the two sodiums, so natrium, sorry, and the iodide. Then you have here all the ions that are important to get some realistic representation of the so-called membrane potential. And here you have the actual membrane. The membrane of these systems is built with some lipids with charge and some other lipids, some other polar lipids that make the calculation, the electrostatic part, a little bit difficult.
Sorry, just to make sure that I understand, this is the transmembrane
Protein.
Protein.
This is the transmembrane protein.
Okay.
No, I try like to use the transmembrane protein. This is the outside. This is the inside. This is some other membranes in order to capture in a realistic way the membrane potential, because the membrane potential is the averaging principle of the whole ions, but not of this little sector. From here to here, you have about 100 angstroms. But an actual cell is micro. It's a lot more. Yeah. and this other leaf of membranes, monocap, is to get a better condition for the electrostatic potential in the boundaries, right? Because one other thing that I like not to say is that you have to add an extra potential here. We put here between 70 millivolts up to 120 millivolts, yeah, which are the actual numbers that every electrophysiologist that measurements in the lab, right? Then once you do that, you do, for instance, a Markov state model to cluster these states, right? And every cluster, the idea of every cluster is like to get these intermediate conformations. Yeah? Then here we have a Markov state model, and here we have what people call TICA, autocorrelations, yeah, independent of time. Actually, like to project in the slowest motions of the molecule, and then you see that more or less you have like 3 big macro states. And you can plot the diameter of the tunnel if you get this macro state, and it's like this, and then you can calculate an actual electrostatic potential for the different conformation, and it looks like this. Okay? And then I have to stop energy surface, and more or less that's it. Okay.
Thank you. Are there any questions or comments?
Yes, thank you very much for the presentation. So what is the, sometimes you mentioned that you use machine learning or artificial intelligence to.
Yes, we are doing that, but not in this thing, because what we do with machine learning is based on those results. And in order to speak about the machine learning results, I need to freeze, I need to present these things.
Okay, and what do you do with machine learning?
We try to. So I say that we do X-ray or cryo electromicroscopy to get these states, right? And the idea of the computer experiment is to get all these intermediate states. But with machine learning, what you do, because we have a big sampling, is, for instance, the first step is to complete this intermediate step, because you tell to the model how to understand the system, and then you project or postulate some other intermediate states. Yes. And these intermediate states are very important to estimate some other macro states to get better the tunnel and to get better the thermodynamics. Because everything is driven to the thermodynamics because of the binding of the iodide, yeah, and the natriums. Mm-hmm. And then you need to get these energies that people get in biochemical experiments.
Yeah. Okay. So to compare to the
Yes,
experimental data.
And that's it. For instance, one thing that is very easy to us for us to understand is that if you need to get some iodide for cancer, you for instance you can get some other companion, some better companionship to help the iodide to bind, to get into the cell. Okay. Yeah? And that is very important. I mean, that's easier to do if you get a better understanding of the intermediate states. Mm-hmm. Yep. Yeah? Mm-hmm. So,
thank you.
When I see the animation of the membrane, I can see that the particles are.
The beginning, the question is what? What is the question from the beginning?
In the force field, one see the long interaction term is a Coulomb potential, right? My question is if it's possible to use a non-electrostatic potential for this kind of system when the particles are very rapidly changing.
Yes, yes. In this actual calculation, we don't use that, yeah? But people do. Some other effective potentials when you need to get what the people are calling now multi-scale model. Yeah, because of the size and time of the simulation. Yeah, you get for instance to trunk the long interaction up to let's say 20 armstrongs or something like that, and from there you do for instance some exponential, something easier to calculate. But what is called multi-scale.
Any other comment or question? Okay, so let's thank the speaker again. And our next speaker, that is Andrea Schialini, is not here, no? Yeah, he canceled. So I think that we do a little break until 11:10. So in that way, we don't mess up the schedule if there is other people that wants to come to the other talks. So enjoy this little break.
Sí, hablar más.
But, ¿esto funciona? No, ¿cierto?
Because again, it's like, you know, these methods are based on seeking.
Lo escucha la gente. Ah, o sea, no escucharon al speaker. Ah, o el speaker lo tenía. Sí. Okay. Ah, bueno.
Ahorita que llegue el otro conferencista que se ponga el micrófono.
Force function. So then you still have a little thing.
Are you Sahid? Yeah. Hi, Alexandra. So, yeah, we have something. Sorry. Yeah, okay. Este es el micrófono de Zoom, ¿no? Sí. Y el speaker, tiene otro. Sí, dale ese al speaker. Listo. Y aquí ya solo está la presentación de él y con el Zoom y todo, y para la gente que está en Gracias.
So again, there's not any problems with spin class though. And making sure what the
de esta, de PowerPoint, del PDF, creo, a ver, el PDF. ¿Qué pasa? Acá. Sí, y ahí está como compartido. Sí. Y este es para las preguntas, no sabía, y otro para el speaker para que oigan los de Zoom. Y con yo brindo.
Yes, this is what I've been doing. Right, so like, I have a thing where I can count the number of inscribed spheres, right? You can generalize this to make it higher. So this is the number of spheres inscribed in the solution. So this will do. You say I want to count the number of centers of these spheres. They're exactly the right distance from the decision boundaries of and in this case, I'm doing the actual solution sets. And don't disrespect any of the limits. You can also do this wires landscape by boosting other requirements that you have so data function all of them. So this is a direction that I'm trying to take. This is also not counting the number of legs, right? I mean, this is one leg that I counted 4 spheres in, right? And we're actually trying to distill whether you're counting one thing, if your legs are convex, and your legs are not convex, it's very hard to mistake them. Convex lake apparently not non-convex lake. Tell me, like, for instance, this is like RSB and RSB find RSB. It doesn't actually tell you whether the solution set is standard. It just tells you it has mass, right? influence on the measure is significant enough to measure, right? Whether it could be mass, this is not actually communicating. They do the same problem you read just here. Even if it finds a measure, which, again, this is the kind of measure which says, there is some number of unique places have a lake of a minimum size, right? I can say that. But how many lakes is a much harder question, because this is one lake where I was able to put several of these standards. This is a measure where a lake is some number of points, which depends on the internal structure of the lake. So it's progress, it's not exactly So I think about line I have no progress on lines. Not as like flat lines, but literally doing complexity of the trajectory between stationary movements or index to like it's like a next order of this is a DMFT testing. You have to solve infinite time. In fact, infinite negative time as well. Because you think of it object, it's not built in sense. You just have to. And this is the thing, it's the problem when you try to do these things too, is like X-rays is all about very clever ways of getting some information out of integrating points integration with configuration space. Integrated configuration space, which somehow knows that this area is also in the same set. It's a very good problem. It's easier to tell further characteristics explicitly there. But that requires that you have set that has a that's only this problem. You have sets that will jagged. Trying to find anything like force theory to disable this.
Está. Fíjate, ¿cierto? Todas estas, bueno, todas. La descarga. ¿Y cuál es la? ¿Esta? Pues, si algo pasa, ahí está. O la abro directamente. O, espérame.
Sure. So this thing of spheres, it's so interesting topological, because you make a graph of it.
Pero espérate, espera, comparto.
Taking accounts whether your space is so this is something, right? It's not understanding roughly, very, very rough.
¿Dónde es que se cierra?
How many groups there exist in this.
Es este, ¿cierto? Bueno, hay más o menos. Bueno, lo bueno es que se traba devolviéndose. Si no la devuelven, no, ni idea quién es. Pues, no sé. Tal vez el que se acaba de levantar. No, the thing is that it's like some kind of bug when you like go back. But
Yes, the thing in the rest of
yes, the only thing that we noticed when we like when from the first slide to the second one, like going back. Yeah. So
All right, yeah, I see.
That one. So we thought that something was advanced, now everything.
Okay, so let's go back to the way it was.
Yeah, right.
Okay, I see.
Okay.
I see how it works. This connect.
Okay, so
Sí copiamos la de John también, ¿cierto? Oh.
I think part of the thing that I haven't been checking, I thought, here, that seems most related to the one, but it's not quite as serious, because the thing of, it's like you developed, even my country struggles, even collaborators, they're trying to compare simulations of the range of gas. It's a model that has the same name as they really distinguish tracer in the space of serial obstacles. It's very similar to the perception, except the RT. And basically, they find these classes using inherent states. You know, what are the inherencies of this model? But the points that start somewhere in space. But when it's so, when you start in space, there's very low margin. Make this very small. And then it's the margin continuously. You find certain places that should where the suspect is most example. So this would be they would call it an iron state. And in fact, in iron states, you find like coincide some of the spheres I can make, but not all of them. They have to be spheres or supported on their boundaries in a certain way. So back to the but I think that means it's more hard to machine. This, it's not even under links with what they connect for the here states. You imagine a lake has a very low margin, it's a big lake, and it's a where they get the to probably too great. And you have to get our states. It's a little closer to but it's not. It's the United States, which is fine by places the solution and vanishes. It's hard. The one that in the archive.
Maybe I should. Okay.
What I understand.
Yeah.
It's for Zoom, so we don't hear here.
Oh, okay, all right. So-
No, this microphone is for the Zoom. No, but this.
Okay, this one.
No, it's for Zoom. Here in the room, no. Ah, okay. The microphone here in the room, because this one is only for the people that is connected online.
Oh, okay, so I
This is for the room.
Please have a wireless microphone. If there's no wireless.
Ah.
microphone,
Oh, that is this one.
Okay, no problem. You.
This one you have to, because other.
People that are online.
You have to, please.
Okay. Hey, is there a point?
We have a.
I saw you have this. Bottom, and when you look at the zero.
Exactly.
Yeah.
So, okay, great, thank you.
When did you arrive? On.
Actually, on Saturday, last Saturday, yeah, I've been here for 1 week almost.
We come back. The talks, so we continue with Sahin Buyukdati.
It's fine.
It's fine, but not correct.
It's fine, it's not correct. It's okay.
So he's actually coming all the way from Turkey, And so we are here very happy to hear him talking about field theoretic formulation of ion correlations with explicit hardcore size in aqueous and non-aqueous electrolytes. So
Okay.
thank you, sir.
Okay, thank you very much. Hi, everyone. So today I will talk about the functional integral formulation of electrolyte solutions. I will present a new formulation of charge solutions that is supposed to improve, upgrade the Debye-Heckel formalism. So let me first present my model, introduce my model. My model is an implicit solvent electrolyte composed of point charges located, placed at the center of hardcore spheres. The hardcore spheres have diameter d. So this also that diameter also corresponds to the closest approach distance, and they are surrounded by an implicit solvent electrolyte. So we don't take into account the explicit charge structure of the solvent. And the standard theory that allows to describe the thermodynamics of these liquids is called the Debye-Heckel formalism. And the Debye-Heckel formalism has several limitations that I would like to illustrate in terms of the thermodynamic functions. So the first two plots show the pair distribution functions, opposite charge pair distribution functions, against the interionic separation distance rescaled by the hardcore diameter. The symbols are the Monte Carlo simulation data, and the dashed curves are the prediction of the Debye-Heckel formalism. And you see that both at submolar salt concentration and at the molar salt concentration, the Debye-Heckel theory is not able to predict the radial pair distributions. The third and fourth figures present a similar comparison for the thermodynamic functions, the internal energy and the osmotic coefficient, or the pressure divided by the salt concentration against the salt density. And again, you see that the Debye-Heckel theory can predict the Monte Carlo data. It can reproduce the Monte Carlo simulation data, which is exact, only at significantly dilute salt concentrations. So there's a clear deficiency of the Debye-Heckel formalism because we see that it is inaccurate at all relevant salt concentrations. Now, what are the underlying reasons? In order to do better than the Debye-Heckel formalism, first we have to identify the weaknesses of this theory. And the Debye-Heckel formalism is based on two major approximations. First of all, it's an electrostatic weak coupling theory. It is based on an electrostatic weak coupling Gaussian approximation. Actually, the Debye-Heckel formalism can be obtained directly from the loop expansion of the partition function or the free energy of the electrolyte in terms of the electrostatic coupling parameter. And at the leading order that we call the one loop level, you obtain the Debye-Heckel formalism. And the second limitation, which is the most important limitation, is that the Debye-Heckel theory has no hardcore size. It doesn't take into account the ion size. All right, so it's a continuum approach. And this is the reason why it fails in particular at the large salt concentration regime, which is dominated by hardcore interactions, hardcore repulsion. All right, so that means that in order to do better than the Debye-Heckel formalism, I have to overcome these two approximations. And the improved formalism that overcomes these two approximations is called the self-consistent Debye-Heckel formalism. In order to relax the first approximation, the weak coupling approximation, I will use a splitting scheme that consists in separating the interaction, electrostatic interactions into two parts, a short-range part and a long-range part. The short-range part is, of course, strongly coupled, so I will treat that part within a virial approximation, and the weakly coupled long-range interactions will be incorporated via a weak coupling Gaussian approximation. And in order to overcome the continuum approximation of the Debye-Heckel formalism, I will directly, explicitly incorporate the pairwise hardcore interactions. So my starting point is the grand canonical partition function of interacting ions. I choose the grand canonical ensemble because the partition function that will result in the grand canonical partition, in the grand canonical ensemble, is easier to work with. It is a more practical form. So the grand canonical partition function, as you know, is the trace of the Boltzmann distribution over the particle positions and fluctuating numbers. And the interaction energy is composed of two types of pairwise interactions: the electrostatic interactions, which are mediated by the Coulomb potential, the 1/r potential. Here, rho c is the electrolyte charge density. And the second type of interaction is the hardcore coupling, which is incorporated via the hardcore potential that is infinitely large if the interionic distance is less than the hardcore diameter, and it becomes zero if it is the interionic distance is greater than the hardcore diameter. So the hardcore potential is defined by this equality. Okay. Now, in order to introduce this variational splitting scheme, I use the formulation. I use the separation approach that has been previously developed by Hatlo and Liu for inhomogeneous electrolytes. So this consists in separating the Coulomb potential into two parts: a short-range part and a long-range part. So this, at this point, this splitting is arbitrary, and that splitting scheme becomes more specific when you define the long-range component, the inverse of the long-range component, as a filter operator, a quartic filter operator, where nabla is the gradient, acting on the Coulomb operator. As you know, the Coulomb operator is the Laplacian acting on the Dirac delta function. Okay, and this filter operator filters out the short-range correlations. And when you inverse this equality in free space, you find that the long-range component and the short-range component of the Coulomb interactions are given by the Coulomb potential augmented by a Debye-like screening coefficient that sets the short range of that potential, and an unimportant sinusoidal function. Now, because, now the question is, what is this sigma? This sigma is the characteristic splitting parameter, the splitting length that tells us what is short range and what is long range. And at this point, its value is unknown. And in order to specify the value of sigma, I will use a variational minimization scheme that I will explain later. Because this particle density representation is not easy to work in, usually we prefer to pass to a functional integral representation of the partition function by introducing an Hubbard-Sretanovic transformation. So an Hubbard-Sretanovic transformation is an inverse functional Gaussian integration. And we introduce an Hubbard-Sretanovic transformation for every single type of pairwise interactions. And because with that splitting, we have three types of pairwise interactions: Coulomb short range, long range Coulomb, and hardcore interactions. I introduced three Hubbard-Sretanovic transformations at this point. And those Hubbard-Sretanovic transformations allow me to recast the same grand canonical partition function in the form of a functional integral over three fluctuating potentials: the potential phi L associated with the long range of the electrostatic interactions, phi S for short range interactions, and phi H for the hardcore interactions. So this fluctuating potential phi H incorporates the ionic hardcore cells. Okay. And the Boltzmann distribution, the new Boltzmann distribution, includes this Hamiltonian functional, which is composed of two types of terms. The first term is quadratic in the fluctuating potentials, and that term incorporates the Gaussian level fluctuations of those potentials whose variance is set by the Bayer interaction potentials: long range Coulomb, short range Coulomb, and hardcore. And the second type, which is the nonlinear, strongly nonlinear term, is the fluctuating ion density. Here the summation is over the ion species. So P is the number of ion species. In a symmetric electrolyte like sodium chloride, potassium chloride, P will be equal to 2. All right. And lambda is the fugacity. And here the exponential corresponds to the Boltzmann distribution of a single charge Qi coupled to the background electrostatic potential and the hardcore potential. So that shows that by introducing these Hubbard-Sretanovic transformations, we pass from a many-body picture, because you know that Rossi and Rouen are composed of the sum of many Dirac delta functions. So we pass from that many-body picture into the picture of a single particle coupled to a background potential that is dressed by many-body effect. So in other words, we switch to an effective one-body picture that is much easier to work with. All right. And with this statistical mechanical formulation, this functional integral formulation, we can evaluate thermal statistical average defined in the usual way. And the first and most important statistical average that we have to evaluate is the pair distribution function. So the pair distribution function associated with the ion species I and J is the statistical average of two such fluctuating ion densities evaluated at different points, at R and at R prime. Okay. And the reason why we have to evaluate the pair distribution function is that, first of all, we can directly extract these pair distributions from Monte Carlo simulations. And then I can compare that with the prediction of my theory in order to determine its validity domain. And the second reason why we have to calculate the pair distribution function is that all of the thermodynamic functions like the internal energy, pressure, the equation of state, and the compressibility, compressibility, liquid compressibility can be expressed solely in terms of the pair distribution function. All right, now there's a problem. The problem is that because this Hamiltonian is nonlinear, the functional integrals cannot be evaluated exactly because here we have the exponential of another exponential, and we are unable to evaluate, to track nonlinearities beyond quadratic order. So at this point, I will introduce an approximation, and this is where I introduce my splitting scheme. And my approximation, I don't have enough time to discuss the details. So the main point of this approximation is that I track the short range hardcore interactions and electrostatic interactions that are strongly coupled within a virial approximation that allows to overcome the weak coupling Gaussian approximation, simply because the virial approximation is a different type of approximation. And the long-range interactions, I treat them, I incorporate them via a Gaussian approximation. Finally, that unknown splitting parameter sigma that tells us what is short range and what is long range, I determined that variationally by taking into account the invariance of the ground potential of the system. Actually, that sigma has been introduced artificially, which means that the ground potential, the ground canonical potential, the ground canonical partition function, they don't depend on sigma. This implies that if you take the derivative of the ground potential with respect to sigma, that will vanish, right? So the crucial step here consists in evaluating this derivative with the functional integral representation of the ground canonical partition function, which results in a variational equation whose numerical solution yields the specific value of sigma. That's it. So this is how I specify the value of sigma by forcing the stationary state condition to the ground potential of the system. And here are the results. So the upper plots show the opposite charge pair distributions and the lower plots the similar charge pair distributions at different salt concentrations that are increased from left to right. So the salt concentration is changed from 50 millimole up to 2 molar concentration. Again, the Monte Carlo simulation data are the symbols. The prediction of my self-constant Debye formalism is represented by the solid curves. And the comparison is made here for 2 different hardcore sizes, for 3 angstrom and for 4 angstrom. So 3 angstrom is black and 4 angstrom is blue. And you see that for these 2 different hardcore sizes, from dilute to molar concentrations, the theory can accurately reproduce the pair distributions. Much better than the Debye formalism. And I would like to say that there is no fitting here. I fit nothing. I calculate exactly what is simulated by the Monte Carlo simulations, and the Monte Carlo simulations simulate exactly the grand the partition function that I calculate within this self-consistent formalism. So next is the thermodynamic functions, the internal energy, the equation of state, and the effective screening parameter renormalized by the Debye screening parameter against the salt concentration. Again, we see that the theory can accurately predict the Monte Carlo data from submolar into molar salt concentration. So for the internal energy, the theory breaks down at about 2 mole, and for the osmotic coefficient at about 3 molar concentration. So in these plots, I compare theory and simulations for the internal energy and pressure plotted against the packing fraction, ionic packing fraction, for different hardcore sizes that I change from 14.3 down to 1.2 angstrom. And the plot shows that the theory can take into account the solid size, hardcore size dependence of the thermodynamic functions within this biologically relevant packing fraction regime over almost an order of magnitude. So the theory breaks down at these atypically small hardcore sizes where the electrostatic coupling is too strong. Okay, so I'm running out of time. Okay, finally, the comparison with experiments. In these plots, I compare the prediction of my formalism for the osmotic coefficient against salt concentration with experimental data obtained for different type of aqueous electrolytes, the upper plots, and non-aqueous electrolytes, characterized by low dielectric permittivity. Now, with a low dielectric permittivity, you increase the coupling strength. So that's a good test for the theory. And we see that by using the hardcore size as the only fitting parameter, which makes sense because the theory, it is compatible, consistent with the simplicity of the model. This is an implicit solvent model. All right, you see that the theory can accurately reproduce the non-uniform salt concentration dependence of the osmotic coefficients and also its variation with the dielectric permittivity of the background solvent. All right, to conclude, I show that this self-constant debacle theory that incorporates explicitly the hardcore size can accurately reproduce the thermodynamic functions obtained from Monte Carlo simulations from submolar up to molar salt concentrations. And it can also take into account the hardcore size, the variation of the hardcore size, the solute size dependence of these thermodynamic functions over almost an order of magnitude. And the same applies to the comparison with experiments. I show that the theory can reproduce the non-uniform salt dependence of the experimental osmotic coefficients and also its variation with the dielectric permittivity of the solvent quite accurately. So this first version of the theory assumes the same hardcore size for all ion species. The next step will consist in generalizing the theory to include the individual hardcore ready for each species of the electrolyte. Another important extension will be, of course, that to confined electrolytes. So the present version of the formalism can be directly generalized to confined electrolytes, in which case the theory will provide us, for example, with a hardcore size augmented Poisson-Boltzmann equation. Thank you.
Thank you very much for your presentation. Are there any questions or comments?
Which one?
Thank you.
Thank you for the talk. Is there something I didn't understand? It's when you have this transformation with the Hubbard-Stratonovich, why don't I would expect that the different fields that you introduce, the auxiliary fields,
Here,
they will couple between them, but I see that they don't couple.
They don't?
They don't couple between them. For example, in the quadratic part, I would have expected some non-diagonal.
They are coupled actually, because if you Taylor expand the exponential.
No, what I mean is, for example, in the quadratic part with the potential.
That's because
it's like a diagonal quadratic form, and
exactly,
why do you have crossed?
Yeah, but this is what Hubbard-Stratonovich transformation is.
But with all the field,
you introduce a separate Hubbard-Stratonovich transformation for each type of pairwise interactions.
Or maybe what
there cannot be any coupling at that level. The coupling is, so this part is the free field.
Yeah, okay.
This is free field. The coupling comes from the nonlinear.
Well, that part I know it well. Or maybe
so
in the previous slide, why you have the, or maybe.
So this is actually the kinetic part, or the graph phi part, graph phi squared.
Yes,
the mass term is here.
Yes. Or maybe what I didn't understand is in the previous slide, how you do the separation between the rho that you call C and rho H for the density. How is it done? For in the energy that you in the previous equation.
The thing that defines I replace VC by this sum.
Yes.
Which results in two types of pairwise electrostatic interactions. Then I introduce a separate Hubbard-Stratonovich transformation for each of them together with the hardcore interactions.
Yeah.
That makes three Hubbard-Stratonovich transformations.
Yes. Okay. How you define the densities, the rho C and rho H?
These are the standards.
Because there is only one density. So how is the separation that you have done?
Well, the thing that I call rho n r is just the sum from 1 to n of delta r minus Ri.
Okay,
Okay, where Ri is the actual ion position.
yes. And
And the same for rho c. For rho c, I'll have here a factor of Qi.
sorry?
Sorry. Okay, for rho c, I'll have here an additional factor of Qi, which is the valency.
So one is the charge density and the other is the numerical density.
Yeah.
Okay. Okay.
Okay.
Are there any other questions or comments?
As I remember, for the Debye-Huckel theory, is essential to arrive to the Poisson-Boltzmann equation, right?
Can you repeat the question?
As I remember, the Debye-Huckel theory is essential to deduce Poisson-Boltzmann equation. You can do
The actual Debye-Huckel is strictly speaking first of all, here I talked about bulk electrolytes, so there is no surface. Whereas the Poisson-Boltzmann approach usually applies to inhomogeneous electrolytes, like an electrolyte in contact with a charge plane. Okay, so it's not the same thing. But the Debye-Huckel formalism corresponds to the linear limit of the Poisson-Boltzmann equation.
But there can be an extension of the Poisson-Boltzmann equation with this kind of distribution of the ions in the solvent?
Well, this is actually the next step, but this formalism has been applied only to bulk electrolytes. So at the next step, I will confine my electrolyte into a nanoslit, a cylindrical pore, in which case there will be additional boundary conditions. And for that type of system, for that type of confinement, I will get, as I mentioned at the end, I will get the hardcore augmented version of the Poisson-Boltzmann equation.
Okay, thank you.
Okay, are there any other questions or comments? So let's thank the speaker again. And our next speaker is John Freddy Mateus, that is here, I think, yeah. I will check it. And you can check if it's okay soon. Like I think. I need to see how did it. Okay, sí. Gracias. Okay, so our presentation is by John Mateus, and he's going to be talking about two-point correlation in Dyson gases out of equilibrium.
Okay, thank you, Professor Alejandra. Okay, good morning for everyone. Thank you for coming here to this statistical workshop. My talk is about the two-point correlation in Dyson gases, and is part of my doctoral thesis with Professor Gabriel. So, okay. So this is the outline of this talk. We start with a brief mathematical description of this model as a Coulomb gas, or mathematical framework to address the main question of the talk, and some developments and numerical results of the of the system, okay? Finally, we show the simplest case of for n equal to and beyond of n. So our start our physical systems is a set of n particle charged particle in a two-dimensional space, okay? So the interaction potential between the charge has a logarithmic form through from the Poisson equation in two dimensions. So we put the particles in a thermal bath with a temperature T and drag coefficient F, and for the consistency of the repulsion, natural repulsion of the charge, we put a electrical background to maintain confined the systems in this space. So we need to work with an inverse effective inverse temperature. This point, beta as q squared upon k Boltzmann T. So large beta means that interaction domain and strong correlations between particles. In the other hand, small beta means that noise term due to the thermal fluctuations dominate and we have weaker correlations. Okay, so we know that in equilibrium, the stationary distributions grows as the Boltzmann factor, where W represents the total energy of the system, right? So the idea is analyze the time evolution of the system from an initial state to a stationary state, right? We start with the stochastic Langevin equation in an overdamped limit. So the inertial term, mass times acceleration, drops out. So we can start with this equation. The first term represents the drag between particles, the interaction term, and the noise term. The noise term is modeled as always mean 0 and delta correlate time for the noise. We established after from the stochastic Langevin equation, the Fokker-Plancke equation, and finally we pass through a Schrodinger form to analyze theoretically this system, right? This is our theoretical frame. So the next step is maps the system into a circular domain. This is a Dyson gas. So this mapping allows us to work in a more simplest case because we only need to know the angular position of the particles. And the idea is ask how correlated the particle's position is. Okay, the Langevin equation to this system in this circular domain has this form. This is the interaction term due to the logarithmic interaction potential. And this is the noise term. This equation is rescaled to work with a dimensional units. And the noise term follows the same rules that the initial noise term, okay? So this is the equation which allows us to simulate the system to get the numerical results. And the next is write the Schrodinger equation of this system, right? So after all calculations, we have a time evolution of the wave function and a gap of energy plus an interaction Hamiltonian and the kinetic term, right? This energy depends on the size of the system and the beta parameter. The Hamiltonian interaction term has the interaction potential and the beta factor as and the size of the system. And if you note, for the interaction Hamiltonian, if beta is equal to, this term drops to 0, so the system has not interaction with particles, behaves as a free system, okay? So we work in this regime. So if beta is equal to, our Schrodinger equation to work has this form, no? After all calculation here, the gap of energy and the kinetic term, okay? So this is a free particle systems, and we need to know the symmetric properties of the wave function. So if we analyze, if we analyze the Boltzmann factor, okay, if we analyze the Boltzmann factor, we need to know that the probability distribution to get the particles at determinate position, angular position at time t, needs to be symmetric form. So with this condition in mind, we need to know that the wave function needs to be a symmetrical form. So this means that this wave function is asymmetric, and then we work to free fermion problem, okay? With this ideas in mind, so we solve the Schrodinger equation with these ansatz. So the energy takes this form. So n sub k means the normal mode, so the system, and the wave function has this form, okay? Here, this term is a spatial term, so this means that we have a determinant of the spatial wave functions, Slater determinant. So here it is. This is a matrix, so this is the determinant of this matrix. Individual wave functions here has this form, depends on the particle position and the normal mode of the particle key. And the expansion coefficients are the projections of the spatial wave function upon the initial state. So we need to set an initial state to can solve this equation. The Fokker-Planck equation gives to use the probability distribution to find all particles at position θ1, θ2, so on, θn, codified in this vector theta at time tau. Okay, here Q sub n is given with this. So this can be in a determinant form. So, and the determinant of the spatial wave function here. So if you note in this equation, we need to know the initial state of the particles. So we work with this configuration at time 0. We have the perimeter of the cycle, and we get a partition, regular partition of this perimeter in n subintervals, and then we pick up a particle here in each subinterval with a probability which follow this rule in an uniform probability distribution. So we choose a subinterval, which is given with that. So we pick up this particle here with this probability. So the initial configuration, the system. So the jump probability for all particles is given because due to the all permutations and the sum of these permutations. Well, our interest is how are distributed spatially all particles. That means if we choose a pair of particles of my system, which is the distance between these particles. So that means that we can choose two particles that are Fitts neighbors, or we can choose two particles with one particle in middle of them, or two particles in middle of them, and so on, so on, so on. So this graph represents the probability that of get these configurations. Okay, so here m equals 1 means that we can choose we choose two particles that are first neighbors. M equal 2, two particles with one particle in the middle. M equal 3, two particles with two particles between them, and so on. Okay, this is the initial setup of the system, and we can write the variance of the system in this form because we know the probability distribution of the situation here. S means the distance between the two particles that we choose. So what happened for the ground state? Okay, for the ground state, we can set infinite points, empty points. So we locate in the fields n points all the occupation numbers. So this configuration represent the ground state configuration. So this n can give us the total energy of the system. If we choose this configuration, the total energy of the system in the ground states gives 0, as we expect. So the rule for choose these sequential points is given by this equation. So we can set all positions and characterize our system in the ground state. So the spatial wave functions in the determinant form takes this form. This is a Vandermonde determinant, and this is very important for the developments that follows because this Vandermonde has many important properties of for the system. So explicitly, we can write this determinant in terms of variable Q or as a Vandermonde determinant. Okay. As we can know this expression here, we can find the probability distribution to find all particles at position θ1, θ2, θ, etc. For the ground state. So this is very important to use because this form of the Vandermonde determinant can get kernel of the system, right? The time is very fast. So, okay, sorry. Main results. How characterize excited states? If you note here, the idea is can solve these Vandermonde determinants for each excited configuration. We can do the calculus. It's very long calculus. So this the main configuration. For example, for the first excited state, it's move of points. So we can get the different possibilities that we can choose in points in these empty points. So after all, and calculate all expansion coefficients, we can find the probability for this first excited state. We can do that for the second excited state, and the result is 0. Amazing, but 0. So we need to move to the third excited state, that this is the configuration, and we can stop here and write the all probability distribution that is given by this equation here. So this is the contribution of the ground state. This is the contribution of the first excited state, and this is the contribution of the third excited states in terms on this kernel. But it's very interesting here because this kernel has many important properties. Once we know this probability distribution, we can move to calculate the 2-point correlation distribution here, right? So this is our result up to excited state. So we can study the case with the variance of this distribution to two situations. The simplest case, which is n equal 2. For this case, we can or complete set of analytical results. So the model works very well. If you not here, see, okay, but the main idea is move to n greater than 2 case, right? For general n. So this is the case n equal 2, n equal 3, n equal 4, n equal 100. So the evolution, these plots show the evolution from the initial state to the ground state or stationary state. And these curves here, that if you can see, represent the time evolution of this distribution here. So if n is more and more graded, we can lose the prediction to the path of the evolution of the system. So here is the variance of the time evolution of the correlation function. And note that these vertical lines show up the characteristic time where the system can be interpreted in the stationary ground state, okay, here. So some conclusions. We have a complete set of solution for n equal 2 and beta equal 2. And we can characterize the relaxation time that this time scales as 1 upon n. So the next step is what happened with beta different 2 and different initial conditions and quench. So sorry. Thank you for your attention. Questions?
Okay, thank you for the thought. Are there any questions or comments?
Are you planning to, thank you for the talk, yeah? Are you planning to make also some computer simulations to verify the theoretical results?
Sorry, again, please.
Are you planning to make computer simulations to verify the theoretical results?
Again.
Ah,
Or in Spanish, please.
sí. El trabajo es teórico, ¿no?
Yeah,
¿Has pensado hacer simulaciones para comprobar los resultados teóricos?
tenemos simulaciones.
Ah, ok.
De hecho, los puntos
Sí.
son los resultados numéricos de la
Ah,
simulación.
ok, perdón. Gracias.
Sí, sí, sí.
¿Alguna otra, any other question or comment? Okay, if not, so we finished this morning session and now there is the lunch break. So and see you at 2 p.m. to continue with this.
Thank you.
Thank all the speakers.
Sería bueno tener un relojito aquí.
Ajá, sí.
Listo, profe. Tocó correr.
No, es al contrario, se verifican las simulaciones con cálculos exactos.
Ah. ¿Qué más, profe? Corre.
My laptop way next to my and too small, it's kind of right. I guess the EROM is it's too slow. So that's the slow. So I defined in the source code the sort of configuration concept. Yeah, I didn't feel bad. Because it was obviously just the configuration. Not have one. You know? Yeah. That doesn't. So I knew like.